Welcome to the New York MariaDB Server Fest 2020. Bienvenidos a Nueva York, bienvenido a Nueva York. I'm looking forward to 3 days devoted to users of MariaDB Server, the open source relational database management system, a fundamental building block of the Internet of modern applications on-prem and in the cloud. The conference is hosted by the MariaDB Foundation, a non-profit that promotes the openness and adoption of MariaDB Server. This is the moment that we've been waiting for. It feels good to stand here in front of a big crowd. Well, that's what I would say if this were a face-to-face conference. Now I'm sitting in front of my laptop in Grankulla, Finland, but I'm still excited. What I'm excited about is to work on the adoption of MariaDB Server with you, the database administrators, DevOps and developers of applications based on MariaDB. In our previous unconferences, we've been working on code contributions from those developing MariaDB Server itself at IBM, Microsoft, Alibaba, Tencent, and our other sponsors on top of the MariaDB Corporation roadmap. So this is a virtual conference, and we have a couple of innovations for you based on attending other virtual conferences the last months. First, we have the conference 3 times in 3 different time zones so that you can attend it daytime. We have material for 2 long days, but we decided to spread it out over 3 days so you can get other things done. Second, we have pre-recorded the conference. This makes timing easier and hopefully sound quality better. And it makes subtitles better, which should simplify understanding of both native and non-native accents. Third, and most importantly, interactivity over Zulip chat. The presenter is available with full attention to take questions throughout the presentation. Read our Zulip instructions on mariadb.org/zulipfest. It should take less than a minute for you to set up a chat account and then join the MariaDB Server Fest stream. The stream is separated into 1 topic per presentation, so you can chat freely on a topic even if the next talk has started. I'm excited to see how this works out. And whenever you have questions, ask us on Zulip to get your problem solved. But if you forgot about that and don't know, you should look at mariadb.org/fest2020. We keep that one up to date with the most recent things and exactly for the time zone and venue happening right now. But now for today's agenda. It is color-coded. We have picked different colors for different topics. So yellow is the first color here is for use cases. Users presenting how they've used MariaDB Server. The first one is by Dupes Dulipa Vijayawardana and Victor Dupshevakka from Supermetrics. Supermetrics is Finland's hottest startup right now, and they have had the task that many of you have, picking the right database. So their story is about Supermetrics and the many bears, a modern-day fable on the search for the perfect database. That will then be concluded by a Q&A session, but remember, you can ask them questions all the time. They will be there to answer throughout the presentation. The Q&A at the end is a summary and perhaps a couple of new questions asked to them. Our second presentation is coded gray, and gray stands for community, so it's the thing that is most closely related to the unconference type of topic that we had earlier. This is by our chairman, the chairman of MariaDB Foundation, Eric Herman, who works for the Foundation for Public Code. So that's a foundation, another foundation creating open source software for municipalities, for governments in Europe, and that has a dynamic ecosystem, a dynamic community. He's comparing that ecosystem with the one of MariaDB Server. An exciting presentation to look forward to. Number 3 is a RED presentation. RED stands for hardware. So this is about the integration of MariaDB with some particular hardware, in this case SSDs. So it's Tong Zhang of ScaleFlux presenting how MariaDB meets solid-state computational storage drives, higher performance at lower cost. After that, we've got blue stuff, and blue is for functionality, blue is for features, and the first one is by Federico Razzoli, and it's about temporal tables, a feature that started in 10.3 and was extended into 10.4, and he will present what temporal tables are and how to use them and why they are of benefit. We continue then with blue, Sergei Petrunia, about Analyze. So Analyze is a tool that helps you see how the optimizer of MariaDB Server works, so that you can trick it into or help it solve issues quicker or get a faster response time for your queries, improve performance. Analyze for statements, MariaDB's hidden gem. Then we turn green, and green stands for best practices. The first one could actually also almost be blue, because it's about MariaDB 10.5's features, but specifically for troubleshooting. It's by Valery Kravchuk, who works on the support of MariaDB Server at the MariaDB Corporation, and he'll be talking to you about how to find the hotspots, the troubles in your own application. And he will then continue with another really hot presentation, dynamic tracing of MariaDB Server on Linux problems and solutions. So I heard this presentation already once at FOSDEM, the free and open source developers meeting in Brussels in February this year, and it was the atmosphere in the room was vibrant with some of the most senior users of MariaDB present, listening how to instrument your application in a near production environment or production environment, so that you can do profiling of what's happening internally on Linux in your application, which is needed if you wish to solve issues that occur rarely and cannot be reproduced in an easy way. It's highly technical, highly well prepared, and very, very interesting. The day is then concluded by Seth Shellnut about a storage engine. So the storage engine architecture is what's setting MariaDB apart from many other databases. We have 2 layers. The first layer is about the SQL syntax, the protocol layer, and the second layer is about the storage. And the separation of those 2 layers mean that you can optimize your application for various different workloads without changing the database. It's the same MariaDB database, but the storage is adapted to the particular workload. And in this case, it's MyTile, a cloud-native storage engine based on TileDB. So that concludes day 1. I'll be back with a summary of what's happening day 2 tomorrow the same time. But now let's get MariaDB Serverfest 2020 New York going.
Welcome to Supermetrics and the Many Bears, a modern day fable about searching for the perfect database. So this presentation from us is kind of a bit weird to do, right, Victor?
Yeah, COVID and all that.
Yeah, I mean, normally we'd be in front of you in an audience, you'd be looking at us, you'd be waving at us, you'd be giving us questions and things like that. We can't do that. We kind of broke into our actual office and are presenting this to you together so that we can have a conversation with you about looking for the perfect database in our organization and some of the stories and the problems we had. And we'd love for you to ask questions of us afterwards so that you get the most out of this. But certainly we decided that the story format was better than trying to have lots of screens. So the deck itself is fairly short, but the conversation we're going to have is going to be much longer. And obviously it is a bit strange talking at our computer screens rather than to you all. So if we stumble, we'll probably pick each other up and go on from there. So first of all, I'd like to introduce myself. My name is Dupes. I have a very long name. I'm a software and data geek, and I started out started out a very long time ago, but I worked for a company called Bioware, and then from there to MySQL and Sun. And then I started my own startup, Empire Avenue. And then somewhere along the journey, I discovered this incredible startup that our CEO, Mikael, had started and joined the company about 3 years ago here in Finland. So we are presenting this to you, the depth of the night in Helsinki, Finland.
My name is Victor. I also have a background as an entrepreneur and a software developer. And I've been at Supermetrics for about 4 years now. And the hair has grown about the same pace as the company, as you can see from the old photo.
And actually, when I started, we were about 9 or 10 people. You had just started 3 months before that. And now we're in 3 countries and 120 people and an amazing growth story and one of Finland's incredible growth startups, if not one of the fastest growing companies in the Nordics. So with that being said, Victor, why don't you give us some information about Supermetrics?
So a quick intro to what we do. Basically, we bring data from one place to another, and that sounds very, very simple, right?
Extremely simple.
But the reality is not that simple. It's a lot more complex than that. We integrate with over 60 different platforms. We call them data sources. So mostly in marketing, but also from basically any area. We fetch data from these data sources, process them in our backend, store some data in different types of databases, and push the data out aggregated to different types of tools where our customers do reporting. So typical use case is the spreadsheet tools, Google Sheets and Microsoft Excel, very popular. Data visualization tools, but also data warehouses, especially for the bigger enterprise customers.
Now, you said store data, but in most cases, do we actually store data or?
Yeah, well, a lot of the processing does time. So we do store some data, but that's mostly for caching. So it's the typical situations we fetch most of the data actually from the data source in real time. And that brings some interesting challenges.
So you can see some of the numbers there. There's like terabytes of data being transferred, hundreds of millions of queries, or 75 plus million queries, and something called 3 billion query seconds. What is a query second, Victor?
By query second, we mean a query being processed on a server for 1 second.
Right. So what does that query processing look like?
So here's a simplified overview of what our application looks like. It's a pretty standard setup, actually. We have requests coming in. We put them in a queue. We have workers picking up jobs from the queue. We go to the data sources to fetch the data, and we store that, as I said, in different types of databases, depending on the use cases. and we'll dive more into those different types of databases in a while.
Right, and of course, when we talk about storing, we're always talking about caching in many cases. But of course, we have some data sources where we have to store the data for a longer term cache or a longer term amount of time.
Yeah. So, for example, in some cases, the data source APIs don't provide the type of reporting APIs that we need to gather the data in real time. So in that case, we basically need to fetch raw data from the data sources, store it somewhere, and do the aggregation on our end.
Right. And so the interesting thing about talking about this application is that, I mean, there's a pretty standard stack, as you saw, like a pretty standard tech stack of workers working on things, processing data. I mean, obviously, we can't get into the secret sauce of how all that happens, but in terms of applications, it's not that unusual. And that's actually one of the interesting things about this application is that we have many different types of use cases that we have to deal with. But I think if you want to look at our application as a kind of a mental picture, you could look at it from the perspective of Finland itself. So this is a beautiful country, and I hope after coronavirus is done with and COVID-19 is gone, you get a chance to come here to Finland and visit and come to our office and say hi to us, certainly. But we have in Finland we have something like 30 million lakes. I heard something like that, like a few lakes.
Maybe, but that sounds a bit much. But
okay, so
definitely more than 1,000.
Oh, definitely more than 1,000. Okay, so I think it's like in the 30,000s, 100,000. I don't know, but it's a lot of lakes in this country. It's beautiful, and of course, water flows from lake to lake, from river to river. And if you think about data as that water that is flowing across all these lakes and rivers through an application, then wherever data starts to collect, then it becomes a pool of water, something that you have to dive into, you have to dissect, you have to figure out what's in there. And these pools of data become larger and larger in an application, and then they become a lake. And we all know that trying to cross a calm lake is better than crossing a stormy one. Yeah. Victor has to deal with a lot of stormy lakes when it comes to databases. So our landscape is filled with these kind of pools. And one of the interesting things, and we don't get into this in this presentation, is that when you look at any technology stack, we tend to look at data structures or databases, and these are from vendors like MariaDB or Google BigQuery or wherever. But wherever you have a bunch of data, that is in itself a database and can become a problem for us. And that could be a queue system. So just keep that in mind as we go through this, because it kind of feeds into all the different types of databases that we have. Now, we structured this presentation as a fable, and the fable that we chose was Goldilocks and the Three Bears, because the three bears were testing out all the different beds to figure out which one was the perfect bed.
Wasn't it Goldilocks who tested the beds?
I believe so. Actually, you're right.
But anyway.
But that's because the bears were sleeping in different types of beds. Exactly. All right. So, fables aside, so where does Mama Bear sleep?
Mama Bear is the traditional relational database. So in our use case, this means a lot of MariaDB, it means some Aurora MySQL, and it means Google Cloud SQL. We're a hybrid cloud, so we use multiple cloud vendors and different solutions there.
So what's Mama Bear looking for, Victor?
Well, it's a typical startup scenario, right? You start with a small application, you build a proof of concept. Especially back in the days, the obvious choice for data storage was the relational database. And that's where it all began for Supermetrics as well. But we still use a lot of relational databases, and MariaDB in particular. And the strength there is obviously the ability to do table joins. There's the indexing, which we use very, very much to have performant queries. But apart from that, we don't actually use the more advanced features of relational databases that much, like procedures or triggers or similar.
And that's an interesting thing about us, actually. We use relational databases, but we don't necessarily use all the features inside of a relational database. But transactional, ACID-compliant data is very important to us.
That's obviously very important, yes,
yeah.
for the core application data.
But relational databases have had a problem with us as well.
Yes. As I mentioned, started out small, yes, that's fine, a couple of hundreds rows, maybe a few thousands of rows. But then the business grows, suddenly there's millions of rows, we add new features, joining tables, can be dozens of millions of rows. We do a lot of inserts, we do a lot of updates, a lot of deletes.
Lots of replicas.
Lots of replicas. And especially traditionally the use cases or the type of things that we did wasn't necessarily optimized for relational databases. So other types of database solutions might have been better options there.
And of course, other problems with relational databases for supermetrics has also been we may have databases in different parts of the world. They're not necessarily distributed, and it's hard to deal with multi-master systems and things like that. So management of those kind of systems can be a problem. And then if we go into some of the vendor locked-in solutions, such as AWS Aurora or Cloud Spanner, then, well, we're vendor lock-in.
Hard to be hybrid cloud then.
Yes, hard to be hybrid cloud, and you end up optimizing for each of the cloud vendors that you have, which isn't necessarily where we want to be as a company. So
that's Mama Bear in a nutshell. What's Daddy Bear then?
Oh, Daddy Bear. Daddy Bear's a simple kind of guy. He doesn't like this SQL stuff, and he thinks that we should just be able to get the data out of the thing. So Daddy Bear for us is Redis Enterprise, which is the enterprise commercial version of Redis that you get on open source. And I'll explain a little bit more about that later. We have Elasticsearch, and believe it or not, we have. I'm going to consider Daddy Bear to also be our file systems as well. So
you're kidding, right?
Come on. Hey, you know the system as well as I do. So yes, EFS and Google Cloud Storage. Yeah, like I said, Daddy Bear is a bit simple. So yeah. So what's Daddy Bear looking for? Well, like I said, he's simple. He's not looking for relational data. It's NoSQL data, non-relational, very much key value systems or document-based systems. We're looking at documents or data sets that are 10 bytes to hundreds of megabytes or more in our case. Now, each of the three main areas there, or four things there, kind of have a different use case for us. So, for example, Redis is very much our short-term caching solution in memory as much as possible. Then we have Elasticsearch is actually our metadata layer that we query for our logs and some analysis. And then we have our file systems. And the file systems is, well, there was a reason why we ended up in the file system. And that was because we were trying to store huge amounts of data into Redis. And I don't mean transactions into Redis. I mean like hundreds of megabytes of data into Redis, which...
Hundreds of gigabytes.
Hundreds of gigabytes. Wow, what's a meg? What's a gig? It all comes down to the same thing, right? So we couldn't do that. But we needed to get this data back out. And so we decided to put it into file systems. It actually worked out really well, which is amazing. But of course, the speed is variable. Networking, file I/O, different cloud vendors.
Yep.
Yeah.
But it has its purpose for very big files.
Indeed. And we discovered the efficacy of that. Now, one of the I mentioned Redis Enterprise is because we moved from Redis open source to Redis Enterprise because there's a lot of things that gives us, and there's a story about all of this that comes back to MariaDB at the end of this. So Redis Enterprise gives us the ability to use SSD storage instead of memory so for large files, and this can be very useful in sub-second queries that we need to do. So, but we wanted to share some of our war stories, and one of the war stories actually was fairly recent, and I'm going to mention a few names in our company, Nicholas and Method. They had to mostly deal with this. In their situation, they were dealing with a data source where we did need to store the data. This wasn't a real-time data. We needed to fetch the data for customers. And when we initially did our tests and did the scoping and the specs, we found that it was small bits of data. We could throw it into Redis. I think that was
the natural solution for
absolutely
key value store.
Key value store. It makes perfect sense. In memory, we're going to do that. And suddenly we were doing a test run with actually, I don't think it was just a handful of customers. And suddenly that data set wasn't the 5, 10 megs that we were talking about, actually turned into the 50, 100, 150 megs, which...
Gigs again.
Gigs again, megs, gigs, you know what I'm talking about. And that can be a bit of a problem when it comes to memory and cost. And it strikes at the heart of a CTO's heart here. So what do we do? What did we do? Well, we had to think about it again, and we had to go from a non-relational database to a relational database. We actually had to rethink how the application was working. And this comes down to one of the problems with non-relational NoSQL data structures, is that your application has to deal with that. And in our kind of analytical aggregated, where we're looking at data aggregations, sometimes that is actually not the best way to deal with it. And there is a good reason why SQL was created, and you kind of walk right back. So what do we end up with? We ended up with, in this situation, moving from non-relational to relational.
Back to MariaDB.
Back to MariaDB. We actually walked right back to MariaDB, which was entertaining in that we discovered a lot of ways of improving even that solution as well. So, with that being said, however, next up is
Baby Bear, last but not least. And here we're talking about the data warehouse type of storage. So in our case, a lot of Google BigQuery, but also Snowflake and PrestoDB. And if you're not familiar with Snowflake and PrestoDB, Snowflake is a vendor that provides a data warehouse solution that works across clouds. So at least in Google Cloud, AWS and Azure, whereas PrestoDB is an open source file-based
columnar stored database.
Yeah. Originally developed by Facebook.
Right.
But yeah, it's Baby Bear, but not a very tiny Baby Bear. So we're talking very, very big data here. But the key is that, for us at least, is that we're able to do able to use SQL. Mm-hmm. So we can do table joins, and we can still query a lot of data really fast as long as we do proper database structuring.
But it's not really suited for anything small, right?
Right. There's always a cost to everything, and in this case, both storage and querying can be quite expensive depending on the use case. So it's not the ultimate solution to every use case.
And of course, for us, BigQuery and Snowflake, these are potentially internal databases that we use for internal analytics and things like that. But for one of our scale cases, we ended up going with PrestoDB. And what was the use case there?
Yeah, so there the interesting case was blackout.
And this is what happens when we do this very late at night, kids. No, in this case, we were taking data initially into MariaDB.
Right, so we're working with MariaDB and hit the limits there. The queries were just too massive for MariaDB to handle. And at that point, I think it was Andy, our head of data engineering, who came up with the suggestion that, hey, let's try PrestoDB. It could be a better fit for this particular purpose.
And it was, from a cost perspective, from an ease of use perspective. I mean, we now query gigs. I think we actually query a terabyte of data in there somewhere, and has been quite effective for us. But of course it has its downsides. It is file-based. It does have limitations in changing table structures and things like that. It's
updating data is not really an option.
Exactly.
It's only inserting and deleting.
So there's lots of issues with each of these particular things. But
an interesting point here as well is that we actually use Redis as well.
Oh, right, of course. We couldn't actually just do it just against Presto.
Yeah, so to insert row by row or even like hundreds or a few thousands of row at a time wasn't really an option. We needed to first gather bigger data sets and then push them all, push all the rows at once. So we actually used Redis there for the gathering of data.
And that brings us to whether Goldilocks. See, I did get the fable right? Right? Okay. See, eventually, right. So did Goldilocks find the perfect bed? So let me ask a question before we get into this slide and talk about this, Victor. How do we actually get our data into Elasticsearch, by the way, for our logs?
Yeah, so we push our logs from application level, but we definitely do not push them directly to Elasticsearch.
Oh, whoa. Why not? I mean, come on. It should be able to handle this.
Yeah, but then if Elasticsearch goes down for some reason...
Has that ever happened? Really?
Nah.
No?
Really.
No.
Then suddenly we're out of logs, and the logs are very important for us, so we can't let that happen. So again, we use Redis as an kind of intermediary storage there.
Well, I think this is the kind of the moral of the story, though, in the end, right? So in everything that we talked about, I think this is where we also... So here, so with some stories that we've talked about going from relational to non-relational. But in a lot of cases where we have actually gone from non-relational back to relational, as I've said in the stories, and part of that is we keep coming back to SQL. We keep coming back to the ease that we have with working with SQL, and it's like putting in an old coat, and you just feel comfortable in it, and it's easy to get going. So MariaDB and MySQL has been a constant feature in our lives. I don't think it's ever gone away, and in fact, we're expanding our use. Yeah. But more often than not, we end up with
one form of hybrid solution. That's usually where we get the most performance and the most cost effectiveness and so on.
So, and that's an interesting thing. It's like, so we kind of look at our data structure or the database for a specific part of our application not as one database, but as a hybrid database. One cannot exist without the other. It's not saying that we can just live with one, and sometimes it's three.
Yeah, it can even be all three of them. So, for example, having the final ultimate set of data in the data warehouse, storing part of it in a traditional relational database like MariaDB, and then maybe some aggregated data or very often used data in Redis for the more key value type caching.
And maybe that's the perfect solution. Do you think that there is possibly somewhere out there a perfect solution that we still haven't tried, or that we can use for our scale, like something that is globally distributed, data warehouse, columnar, maybe, or something like that, with a relational database as well, and some document or non-relational stuff, but also non-vendor lock-in across all our hybrid cloud solution. And what am I missing here? Oh, something in memory so that we can use it for key value as well. Like,
it sounds like a dream.
It is a dream. One that, I know there's a lot of people who've tried this, but yes.
To be honest, I don't know the answer to your question, but I certainly do hope that there is or will be. We've been following the developments of SkySQL with a lot of excitement, partly because of the multi-cloud and inter-cloud capabilities that you mentioned. We do use 2, if not 3 clouds, and we need to be able to have the data travel between these clouds. And if we do it ourselves, it means a lot of self-managed databases and a lot of maintenance associated with that. And
we don't have a lot of DBAs, though there might be someone watching that might want to come work for us, right? I mean, there's all sorts of cool things to do here, but I interrupted you, sorry.
Yeah, but no, we don't have like dedicated DBAs, at least not at this point in time. So one option is to utilize the very best knowledge and experience that there is out there in the form of Sky DBAs, and that's essentially a model that we have tried already with Redis Labs, as you mentioned, in the case of Redis. So using the enterprise solution for that.
And I think supermetrics is an interesting use case. I think it's something, and I'll be honest, when I started here, my first thought was, this is going to be simple. We're going to use MySQL, as we already have, MariaDB, of course, plus Redis. Everything's going to be simple. But in actual fact, as we have scaled and as we have grown, we have so many different use cases that like nothing works just as you would like in one single database. And that seems to be the crux of the matter. They always say use the best tool for the job.
Exactly.
And that is true. We can't seem to use the best tool for the job. We have to use the best 3 tools for the same job to do the same query. It is not a joke to say that our application sometimes in one code piece might query the Redis, the relational MariaDB, and the data warehouse type structure within a 20-line span, and combine those 3 things together to give back the data set that we need. And that's a unique point, I think, in some cases.
Yeah.
So.
Yeah, and that's something where, as I said, we're excited about the potential of SkySQL and also the hybrid aspect that SkySQL provides.
But the other moral of this story is, of course, is how important relational databases have become, even though we thought that NoSQL, SQL battles would be waging even now, and our lives would be more NoSQL than SQL. So
we still find ourselves doing a lot of table joins.
Yes, we do. Yes, we do. But hey, you know, one of the interesting things, and I think time is getting pretty short here for us. So we do want to say that Victor and I are basically like the messengers of an amazing team at Supermetrics. I would be remiss to say that that even these 5 names on this list on this slide is just the tip of the iceberg. You know, our thanks to Andy, Dimitri, Nicholas, Metod, Mikhail, and lots of other people. So, and by the way, I just want to put a plug in for Supermetrics and say that we are hiring. So please do check our jobs, but there may even be jobs that we haven't posted. So please do get in touch with us. Thank you very much to MariaDB Server Fest, to Anna, to Kai, to all the wonderful people there. Thank you for having us. It is very strange giving this presentation from this format. Victor and I, you're going to have had a lot of fun trying to set this up today.
Very fun.
So we hope you'll come visit us here in Finland, and looking forward to the questions, and we'll answer as best as we can. It was a pleasure, and see you next time.
Thank you, Victor, and thank you, Dupes. We have Victor Dupsebacka and Dulipa Vijayawardena joining from Helsinki, Finland, right next door. Hi there, and welcome.
Hello. Greetings, Kai. Pleasure to be here with you again.
I see some the last rays of daylight here in Finland. We've all flown across the Atlantic faster than the Concorde does. So now we're happy to be live also in New York.
We're happy to be here as well. And this might be the last rays of sunlight we see for the next 6 months. I mean, we are in Helsinki.
Yeah, well, that's Finland for the others to know, yes. So I was thinking about your presentation and specifically the architecture part of your fable and the many bears. So when you pick a product, you first have to pick the architecture. So how do you pick between things like NoSQL and key value and SQL solutions?
Well, it depends a lot on the data, of course, what data we're dealing with. But a lot of what we do is to just have the data kind of flow through our system. So we cache it for a short time. And in that case, key value store and even file systems, as we talked about, are the natural option, especially if we're dealing with big blobs of data. Then there's the relational database scenario especially when we need to do table joins and combine data from multiple tables. The obvious choice there. And then again, when we're dealing with terabytes or dozens of terabytes of data, we're often looking at data warehouses. But it all depends on the situation and the data that we're dealing with, what we get from the data source and so on.
Mm-hmm.
And we do get it wrong a fair bit of time, unfortunately. And so it takes us a while to get things sorted out in our planning.
That's very true.
So confession time. I was also listening a lot to your mentioning SkySQL or SkySQL, however you pronounce it. So from your perspective at Supermetric, what's really the difference between when you're looking at SkySQL and when you're looking at MariaDB Server?
Well, I mean, fundamentally, they're the same thing. MariaDB for us is the technology behind SkySQL, of course. MariaDB is very important to us. It runs many of our databases, our internal databases that we run. What's important to us when we think about SkySQL or SkySQL is that for us, we don't have a huge operations team at Supermetrics, and we're growing very fast. We're always looking for partners that can help us run or manage our databases, especially in the cloud. We've succeeded with Redis Enterprise, where we've had Redis do our Redis databases, and SkySQL in that situation is very similar. We are very concerned about being not tied to a very specific cloud vendor, and SkySQL is therefore a very valid way for us to deal with that situation. Did I miss anything there?
And getting in the expertise is I think fundamental, because as you said, we don't have dedicated DBAs, at least not at this point. So getting the best people in the world looking at our MariaDB databases, that's
I'm
quite
pretty
attractive.
Sure. Absolutely, and I don't think I ever mentioned, but I think we're hiring. But anyway, either way.
Oh, you are.
It's surprising.
And doesn't have to move to that place that you're mentioning with no daylight in order to work for you.
Well, have a chat with us. You never know how we'll deal with the situation.
So moving back to technology, JSON, how would you describe your usage of JSON? How important is it for you?
Well, most of the data that we're getting in is in JSON, so that's like at the very heart of what we do when it comes to the data transferring. We actually don't have that much use of JSON columns in our MariaDB databases. We have a few, I think, but that's something that we're probably going to have more and more of in the future.
So any other expectations on the JSON support? Like you were now saying, you're not yet using the fact that you can parse these JSON objects and get results from a select based on the content of JSON. But do you have other wishes for the future when it comes to JSON?
Basically the obvious positive with having the JSON in database compared to Redis, for example, is the parsability that you can pick certain properties and search by
which is functionality that already exists in Maria.
Exactly. Yeah. So that's I think what we need first and foremost.
And we have to do all of this at scale and very much in real time in many cases. So that's the key to all of us. We haven't actually looked at the JSON in MariaDB for many reasons, but we do want to. It's one of those things that it's on top of our list.
So I have a meta question for you. You have a little bit more than 1 minute to answer, but what's your reaction now to this MariaDB Server Fest? You accepted giving a presentation here, and now you've seen the interaction over social media, over above all Zulip and the pre-recording stuff. Has it worked? How has it worked for you?
We were just chatting about that before we started this second round, and Victor was saying how this is fantastic from a participant perspective. Yes, it's a little bit more work from the speaker perspective, but it is true. It's a easy to digest format. We do absolutely miss seeing you in person, Kai and Eric and everybody else, and we wish we could be there for the beer. But it is also great to get the information out and talk to people through this fashion.
Yeah, having three tracks with. So you can participate in your own time zone. That's great.
I'm glad you like that. So this is a first for us, and we're checking out how things work. It was important for us to get it to work both with things like subtitles. They're not easy to, not everything is easy to digest without that, and the interactivity that we get through people interacting over Zulip chat has been great for us. So thank you for presenting at the MariaDB Server Fest, now not just in Paris, but also in New York. So any concluding words from you?
We'll see you in Japan.
Oh, thank you.
Thank you.
Bye, Victor. I now have the pleasure to introduce you to the chairman of the MariaDB Foundation, Eric Herman, who will be talking about how to compare the ecosystems of MariaDB and the one of public code.
Hello. Today I'm going to be talking about comparing ecosystems, specifically comparing the ecosystems of MariaDB and public code. My name is Eric. I'm a developer and I have been for the majority of my career. My career has mostly been commercial, although I did work for MySQL from 2004 to 2009. But even during that time frame, a lot of the work that I did was on their commercial proprietary products. So even during that time frame, it was mostly commercial work that I did. That said, I am a long-time contributor to free and open source software projects. You will see commits in MariaDB, in MySQL, in the Perl interpreters, Perl core, as well as a handful of other maybe less marquee projects. I have been involved with the MariaDB ecosystem for a while. I've been serving on the board of directors since 2015. Currently, I am the chairman of the board of directors, so I'm serving in that role at present. Professionally, I work for the Foundation for Public Code as a code-based steward. In my role as a code-based steward at the Foundation for Public Code, I often point to MariaDB as an example, usually as an example to copy, a template that we should follow. But occasionally I talk about it as a counterexample. We don't want to do it like this. And so I'll definitely be highlighting some of that throughout the course of this talk. So first off, what is public code? Public code is the combination of software and public policy that is produced for and by the public. And as we think about it, software is becoming core infrastructure. We see cities collaborating in order to build the applications and services that are essential for them to execute their mission, whether that is allowing me to register for some form of taxation online, or it is for me to renew a permit or schedule a big trash pickup or anything. Many of the things that we expect to be managed by a municipality or by a larger public organization are now software. And very often public policy is being specifically implemented in software. So much like roads and water and waste disposal are all things that we expect public organizations to at least manage, if not run the detailed execution of, software is also becoming core infrastructure. The Foundation for Public Code publishes the draft standard for public code. This is a document which collects the set of requirements that all the software that we depend on as infrastructure should measure up to. Now, if you're a professional software developer and you read through the standard, I expect you will find very few surprises. I think that everything in there is going to read to you like the typical best practice, mostly what you're doing today. If, like me, you don't have a deep background in public software development, then the first time you come across some of the things that are a bit more policy related, that might be new for you. But other than that, I don't think you'll be very surprised. At the Foundation, when we look at a code base, we look at it from the dimensions of quality, community, product, and support. And quality is what I do as a developer. I work with the developers and we take a look at the standard, we compare their code base to the standard, and we say, does it have the quality we expect? But a code base is so much more than just the code, and even more than the code and the developers. There's many more individuals that make up that community, and so it's not good enough to just stop there. We must have a view which is wide enough to encompass all the different people that are either deploying, maintaining, monitoring, running the software, the end users of the software, the citizens for which this software serves. So the community can be much, much broader than the developers who are making the code and the managers. And like commercial software, we expect that there's more than just code sitting in a repository. We expect it to have what's needed to get it installed. We expect it to have what's needed to understand how to run it, that it has the documentation and the other things that a complete product has that not all open source projects have. And of course, you may not be in a position where you want to or where you're even able to install, deploy, maintain the code base yourself. And you may want to contract out those services. And so is there a support network that's able to provide you the help that you need so that you can do what you need to do? And so those are the 4 things that we look at. And in our organization, we don't do advocacy. What we do is we work with code bases to make sure that they are achieving their goals in regards to these 4 areas, but we don't have to convince them. They're working with us because they're already on this road. There's other organizations that do advocacy. The Free Software Foundation Europe jumps to my mind as their Public Money, Public Code campaign. But the organizations that we work with, they've already decided to work in the open doing public code. When I think about the mission of the MariaDB Foundation, they talk about different pillars. They talk about continuity, collaboration, and ecosystem, which I already see some overlap, but one of the things that stands out is I think that they are a little bit broader. And then there's, of course, the mission of the MariaDB Corporation, as well as all the other big contributors that contribute to the MariaDB codebase, as well as all of us as individuals. We don't even have a mission statement necessarily. We're users of the product. So when I'm comparing MariaDB to the standard, or when I'm comparing MariaDB to one of the code bases that I'm working with, there are times when MariaDB has an obvious advantage, and that is that MariaDB has a gigantic ecosystem. There's all the work that's coming from all the developers employed by the MariaDB Corporation, as well as the engineering coming in from the likes of IBM and Tencent and Alibaba and everybody else that has made very, very interesting contributions over the years. And the user community is very large indeed. So we wouldn't expect that if you are a city developing a license renewal website, that even if you're in collaboration with several other cities that have a similar need, that you're going to have nearly the user base of something like MariaDB. We wouldn't expect that you'd have nearly the developer pool of something like the MariaDB server. So it's not always a perfect comparison, and that's not even anybody's fault. That's just because sometimes there's not a match. But one thing that comes up is, are we developing a reusable component? Are we developing software that is more than just going to be used in this one project that can be used in other projects elsewhere? Is it going to have a life that is bigger than this one instance? And this is a great place where I get to compare with MariaDB, because in the case of MariaDB, users start with an application, maybe with a WordPress site. They don't think to themselves, I want a MariaDB database. They may not even think to themselves, I want an SQL database. However, MariaDB is a component that is a default in many Linux systems or other systems. So that's a great example that I can point to, and I used recently when talking about OpenZoc, which is a case management component. And if you're a city and you're developing something which is going to have a case management aspect to it, you don't start by saying, I want this specific case management software. You start by saying, I want to deliver a service. But maybe you're delivering that service according to the Common Ground standard, which is it's a way to write applications that was standard described in the Netherlands. And the OpenZac component fits into that Common Ground standard. And maybe OpenZac becomes the default in that standard. And then anybody developing a Common Ground app maybe will naturally reach to OpenZac as the first case management component that they would use. So that's an example where I get to draw a very close parallel. Another place that I get to draw a parallel is that, of course, collaboration comes with a cost. There's, if nothing else, communication overhead in working with others. But I think about how MariaDB, the development started with one organization. Now we see development coming from many. Of course, there's the majority of development happening in the MariaDB Corporation, but we also see very interesting features coming from other places. And I think about the instant add column, which came from a brainstormed at MariaDB Unconference a couple of years back, and we had developers from Alibaba and MariaDB Corporation, naturally, and Tencent sitting together in a room talking about a way they could do this. And the prototype was actually developed by one of the Tencent developers. So that is something that benefits us all. And even though it was solving a very specific use case that they had, that's now something that benefits everybody. And so that's a great example and makes it parallel to one of the things that I see with the Signalen project, which started in Amsterdam, specific to their needs, and the Association of Netherlands Municipalities started working with Amsterdam in order to replicate that. And then, of course, they needed to change things so that it would be appropriate in some of these other contexts, in some of these other cities they wanted to deploy to. But those changes were also beneficial to Amsterdam. So yes, there's cost in collaboration, but then, of course, the obvious benefit is that the other developers are developing things that are not your highest priority, but you will benefit from. And the first thing that I do when I think about MariaDB and my role is I think about, so how does MariaDB measure up to the standard that we publish? Well, so does MariaDB code in the open? Well, the answer is yes. And when I'm talking to development organizations, especially ones that are just making the transition from working in private or behind closed doors anyway, working in a closed fashion, to wanting to transition to working in an open fashion, they are understandably hesitant about all of the things that can come up. And I get to point to MariaDB and I get to say, hey, they have their public development branches on GitHub. They don't just do a big release at version boundaries and say, here's all the changes since last version. Instead, you see the code unfolding as developers are working on it. And you know what? These developers make mistakes. It's fine. We're not going and pointing at them. We're not holding our bellies and laughing at the mistakes they're making. Instead, we understand that that's a normal part of the development cycle. We all make mistakes. Sometimes we make dumb mistakes. That's fine. They get discovered. We talk them through, and we come up with a solution which doesn't have that mistake embedded in it. And so that's something where, even though it's scary, we can see that these developers don't have to be afraid, because we can point to the MariaDB ecosystem and say, look at the work that's being done there. You don't see that there's really anything to be afraid of there. And it's not that all the code is perfect at all. And one of the things about working in this way is things that we might have been sloppy about, or it might have been just expedient to do something like put some secret data into the repository. Now we know that if we're going to publish this, we can't just, because it's easy or expedient, commit a password here. We have to have good hygiene, have our secrets in a separate location, not in the codebase repository. So there's a natural advantage that comes up that we want anyway. And then as we are working, if we're working in the open and somebody else is working on a long-lived branch or maybe a patch set, if we're working in this incremental fashion, it allows them to track our work again in an incremental fashion. And that allows us to work with a much, much wider range of vendors or contributors or individuals. And the standard talks about building reusable and portable and extensible code. And when I point to MariaDB, I get to say that these are aspects that have contributed to the fantastic success of MariaDB. No matter what operating system you're running, no matter what architecture you're running on, you can run MariaDB. But also, this is a bit of a counterexample, because internally, MariaDB is not so modular. It's not so easy to reuse the bits and pieces. I'm not going to pull the parser out of MariaDB in order to examine the complexity or build a load balancer or something like that. So when I look for examples of systems that are internally well modularized and the pieces are reusable. I point to things like GNOME's glib, where projects that have nothing to do with GNOME are reusing bits and pieces of the glib libraries, or KDE frameworks, very much the same thing, where people who are writing things that aren't even intended to run on KDE are using some of the libraries that they developed to make writing KDE applications and writing KDE itself easier. And this lack of internal modularity is something that I think limits contributions. And I think that this is something that we as an organization, or as a community, as an ecosystem, I think this is something that we as an ecosystem, this is something that we should give some thought to. Is that a place we can improve? Something that's important for all open source code bases, whether public code or not, is that they welcome contributors. And if you are making the transition from developing in a closed fashion to developing in an open fashion, this is really hard. Part of why it's hard is that you probably don't have a lot of extra bandwidth for reviewing somebody else's contributions that are not in your highest priority things to do list. So you know that if you're working in the open, that you're going to have to invest in that. That takes a time commitment. And also, it's not a lot of fun to admit all of your mistakes in public, to have a public bug tracking system that anybody can look at and anybody can read and anybody can see. That's intimidating. And then we need to give serious thought to, okay, how is security issue reporting going to be? What's the right level of transparency for that? And then also, if we're making a public roadmap, which is important for encouraging contributions, because without a roadmap, it's very difficult for me to know whether or not I'm helping or whether I'm pulling the code base back in a direction it doesn't want to go. And so a publicly visible roadmap is useful to all contributors to know how their contribution slots in with the future as it may unfold. But a publicly visible roadmap also starts to feel like you're making promises, and you definitely need the freedom to be able to say, this is what I believe we're going to deliver, but this is not a promise of what we're going to deliver. And so articulating that well is important. So I think there's also room for improvement in the welcoming contribution of the MariaDB ecosystem. And specifically, what I detect is that there's a lot of undocumented tribal knowledge where all of us that are in the ecosystem have a sense of things that are not written down. For instance, one of the things I would like to do is I would like to get together with as many of the senior developers as I can get time with and get them to tell me what they hope to see change in the structure and the architecture of the code base. And then if I collect all of this together, maybe I can present it back to everybody and say, hey, is this our technical roadmap? So maybe that'll happen this year if I can get together with enough people and carve out enough time for that. Related to that, if I'm doing development, where are the engineering guidelines? There's a little bit on style, but in terms of really how one should approach coding, what's the right level of abstraction? When do I use inheritance? When do I use composition? How much should I be programming in a stateless functional style? When is it okay to manipulate as much state as I want? These kind of engineering guidelines, I don't think that we have these written down. This is something that each developer on the server or in each of the connectors, this is something that they know, but is not explicit. So I think we could document that. And also, I think that we've not been good about what our future roadmaps are going to be. But even though we haven't been good about this is still an area where we do naturally share it. Every time I'm at a developer meeting in an unconference or similar, the developers are always sharing what their challenges are, what the things they want to implement are and why. And so there is some knowledge about what is coming on the roadmap. It's just not written down. And so we do share this with each other. We just don't share it in a way that is very easy for people who weren't in the room to be able to learn. And so I think that this is an example where it's perfectly fine, but we could improve. Believe it or not, there's a bunch of code out there running in the world that is delivering a lot of value that is not under a version control system, that has backups with dates and times or version numbers in the file names, but is not in version control. Fortunately, version control is becoming the norm. I think especially thanks to GitHub and GitLab and the others that have made it so easy for those of us, regardless of how technical or not we are, to participate in the forking, modifying, requesting merges, seeing our changes get merged. So I think that these online platforms have made us all better users of version control system. So that's really good. And obviously, MariaDB is up on GitHub. It uses Git. If we go back through the Git history, not only do we see everything since it was transferred into Git, but we can also see the old Bazaar commits as well as the BitKeeper commits that stretch all the way back to Y2K. So that's a good one. I think that's one where we can show that it stands the test of time. And another thing that I work with all code bases on is to ensure that every line of code is getting reviewed. Every contribution, even documentation, everything should have more than one brain review it. That there's the author, and there needs to be somebody that's taking a fresh look at it as well. Let's not have the habit, as convenient as it is, of having the developer write the code, test the code, commit the code, and deploy the code, and have no sounding board to give them the insight that they overlooked something obvious. So this is something with the MariaDB ecosystem that I see is basically true in practice, but we could do this a little bit better. Specifically, we could have protected branches or enforce it otherwise. And there's times when I see request for review happen when it doesn't happen in a timely fashion. So I think we could get better about our responses to that when somebody adds a pull request, although I really, really appreciate how much work that is. And hats off to the devs that are doing that review. And I do understand that you are each very, very busy. When I think about the reviews, another area that I think we can improve a bit is we typically review the code and the tests very closely, but we think of the documentation separate as an afterthought even. And so I would like to see us, when doing some code, to also conjoin that with, and this is the change that's needed in the documentation, so that it's a single unit. And that's a bit of a stretch for us, I think, but that is an area that I think other code bases do better. And there are standards that are relevant to the MariaDB code base, specifically the SQL standard, but also, depending on which connector you're using, maybe the ODBC or JDBC or one of the other standards. And so our reviews of these contributions, are they having somebody look at not only the code and the tests, but also, is this bringing us closer to the standard? Is this unrelated to a standard, or does this bring us further away from the standard? And so this is something that I think I think it's just a place we can improve. I don't think it's a big deal, but I think it is something that we are not making explicit today, even though I think it happens more or less as it needs to on an ad hoc basis. But I think we could be more deliberate about this. And the one thought I had on this is maybe a reviewer checklist would help. I don't know if it would or not, but possibly. And another thought I have is that we don't engage enough people in the review process. People who are not developers absolutely are good candidates for documentation because they will read it as a non-developer, which is fantastic. So let's engage in our ability to do documentation as well as code. There's a lot of code I can't contribute to, but maybe I can contribute to the documentation that is of what that code is doing. So I think that we can increase the pool of people involved in the review process. Now, obviously, if I'm only working on the documentation, I can only sign off on, yes, the documentation for this looks good. I have no idea if the code is well structured, but my part, the documentation looks good. Or, hey, I don't feel like the documentation explains something that makes sense to me. Maybe the code is great. So we have to be clear, if we're only reviewing part of it, what role we are taking on in our role as a reviewer. Continuous integration is something that is important for every code base, and fortunately, due to I think largely we can give credit to the online repository hosting services like GitHub and GitLab and such. Continuous integration is becoming the norm as well, and MariaDB has had continuous integration for a very long time. It's had BuildBot since before there was Travis integrations and such, and BuildBot is continuing to improve. But it could be faster. There's often a big delay between when a branch is pushed or a merge request is opened and when we see the results of BuildBot. So that's something that could be better. Also, sometimes tests fail and then they get rerun and they pass. So there's been some unstable tests historically. I understand that that there's significant effort right now to identify and resolve all of the unstable tests. Maybe that's maybe that's done now. I don't know, but that's something that I think is something that needs attention continuously. Also, test coverage is something that we don't report in the MariaDB ecosystem. So it is possible to run test coverage utilities, but we don't currently. And as a reviewer, when I'm reviewing code, I want to be confident that the code doesn't break anything, and what I'm reviewing is the structure of the code, is the clarity of the code. I don't want to have to, as a reviewer, try to be a test engine in my own head, imagining every corner case and branch condition. I would very much like to have the test suite give me confidence that the code works, so I can focus on, is it well implemented? Many code bases are doing now is they're saying you can't merge to the main development branch unless all the tests pass. And that's something I would like to see us be able to enforce in the MariaDB server code base as well, which we don't today. Documentation is an area that I think we can all participate in. So please contribute. The Standard for Public Code says you should document your objectives. Well, that's something that I think we do a reasonable job at. I think we could be more explicit about that, especially around which versions of the SQL standard and especially around to what extent we expect this database to work as an upgrade path from another database or similar. Document your code. Again, I think that if you're a developer, you're already doing a pretty good job of this. Obviously, this is something that I think few of us would say the documentation across all of the server and all the connectors is as good as we'd like it to be. So I think that that as you're working on code, also take the time to contribute to the documentation there. Use plain English. This seems really basic, but remember that not everybody reading the code is necessarily going to be a native English speaker, and therefore the documentation, whether that's in the code or on the website or anywhere the documentation is, please do your best to write it as simply and as clearly as you can. And the goal for the documentation should be to communicate. We don't have to show off how poetic we are. So anyway, use plain English, please. And I would say on the whole we do pretty well here, although I think I would like to see the per version information improve a bit, because when I'm running a particular version of MariaDB, sometimes it's not as easy to figure out which features I have and don't have. So I think there's an area there where we could improve, and there's examples we can look at in other software where they have that same kind of thing. So I think we can look at others and learn from them as well. Code-based maturity. Hey, Code-based maturity is an area where MariaDB, I think, does very well. The version numbering makes sense. It's very clear to understand when something is a release candidate or when something is prime time. So that's really good. And also the change logs are always informative and are good to give me the update I need for what changed in this version. So overall, there's a bunch of areas that I would like us in the ecosystem to consider when I look at the MariaDB ecosystem and the MariaDB server code base especially, and I compare it to the draft standard that the Foundation for Public Code is publishing. I think there's some areas that this causes me to highlight as areas we could improve, and I've talked about them, especially around documentation, reviews relative to the various standards. Can we get some branch rigor? There's more we can do in terms of testing and roadmap. Let's get some engineering guidelines together. Maybe I can work on that. And obviously the internal modularity, I think that's the most difficult one. But with all of this, most of the time what I'm talking about is we can do it the way they do it over there in MariaDB. That's a community that is doing a lot of things really right. So thank you very much, and I understand we're going to have some question times now.
Thank you, Eric Horman, the chairman of the MariaDB Foundation, but here speaking as representative of the Foundation for Public Code. Great to have you here.
Thank you.
So I have a couple of questions for you, several ones actually, but first I'd like to make a couple of, shall we say, housekeeping announcements and a couple of questions for the audience. And that's related to our interactivity. So we have a chat going on Zulip chat. And first of all, a reminder, every single session here has its own topic in the stream of the MariaDB Server Fest 2020. And everybody's welcome to chat there. The question is, now that we're actually in New York, in the New York time zone of the MariaDB Server Fest, there's already a seed in all of these topics, or most of these topics at least, from when the conference was on the other side of the Atlantic. So I would welcome everybody's comments on what it feels like to join a conference that is sort of the second time happening in a very short time. Is it a benefit that you have some seeded questions? Do they help you? Please answer, please come with comments in the Zulip chat itself. And perhaps you, Eric, do you have a comment on this?
Well, the thing I noticed right away was that there was a little bit more silence on the second go around, and maybe that's because there's fewer people handy, but I expect that that's in part because questions that somebody might have arise in their head, they can read in the scroll back, and so they already see a good answer to. And what has come up in this one were indeed things that were not covered in a previous session. So, for instance, Federico asks, "Hey, is there a reason that BuildBot doesn't have the test coverage in it?" And that was a new question. It wasn't something that was asked in the previous session. So, and so I think that there's probably going to be a trend of a little bit fewer questions, but I don't know. I've only seen 2 now, so I'll revise that opinion as I have more info.
Right. No, we're excited to learn from this, and I think the basic idea here being that you can ask questions during the presentation, and then you're sort of at the podium now, and when the next presentation starts, you'll still stay at the podium, and people can approach you over Zulip, and you can give your answers and your attention still while the next presentation has started.
Yeah. And in fact, I I'm fairly surprised at how well that's been working. And I was a little bit skeptical of the format when it was first presented to me, but my experience now is much more positive. I think this is, well, of the online conferences I've participated in now in the last few months, I've been to 4 or 5, and I think this is the best formula I've seen so far. I'm sure there's plenty of things we can improve, but I think this is a step up from the others I've attended.
Great, thank you. So looking at what we did before, we did unconferences, and unconferences to us mean 2 things. First, it's a more spontaneous format. There's little spontaneity in this format. We just have a slot for questions where there's a Q&A, the one that we're doing now. But unconference for us also meant, perhaps not in the word itself, but the type of conferences we had were directed at developers of MariaDB Server itself. And I think your presentation now here was one that was most like the conferences we've had before. Would you agree?
Oh, yes, absolutely. I think that when I learned that we weren't going to have an unconference this year in the typical sense, because obviously it doesn't make sense, and these were the things I wanted to talk about with the other developers. So that was why I decided that this would be something I could talk about to the broader audience. But indeed, I think most of the ears I was hoping that would tune in would be more of the contributors, whether they're developers or even people doing bug reports. But I think that I was hoping to reach at least some of the contributors that would maybe some of these things would resonate with them, especially the areas that I think we can improve.
Right. So speaking of contributors, the role of the MariaDB, or the mission of the MariaDB Foundation, is twofold: openness and adoption, where openness looks at code contributions and actually the developers of the server. And that has been our focus in the unconferences, as I said. The other focus of ours is adoption, which is what we're looking at now, the users, the DBAs, the developers of applications based on MariaDB. And you were very explicit that you don't really do much of that at the Foundation for Public Code. You say that, well, other people are doing the convincing that open source is a great thing. Well, I don't think we're doing much of that convincing at the MariaDB Foundation either. We're not convincing people that you should do open source, but what we are convincing in our adoption is that since you're doing open source, since you think open source is a great thing, when you do relational databases, use MariaDB. So do you have that kind of, shall we say, adoption work where you say, hey, the applications that we have here that we've helped build in the Foundation for Public Code, they are great?
So yes, similar. Not precisely as you describe, but one of the things that the code stewards at the Foundation for Public Code do is work with the maintainers of the code base, and those code bases all are going to have a website. And in my talk, I spoke about a little bit the difference between just a project and a real product, something that has everything you need to understand what it is, why you might want to use it, how to install it, how to run it, how to maintain it, all that stuff that's very important. And so our code base stewards have worked with the people who are authoring the software to work on, hey, let's get the website for your software up and running. And although they won't do the advertising, but they will advise on what will help with search engine optimization, what will be important for just clarity so that others can understand the message. And so there is that level, but it's still, again, it's going to be much more of a coaching role rather than actually doing the advocacy for these code bases.
So I have one final question for you, and this is related to sort of the commercial aspect and the roles here. You were mostly mentioning civic units there, entities that are governmental. What about commercial players? Do you have anything to say about their role?
Indeed. So most of the time, or at least much of the time, software that's being developed is maybe being managed, or it's being specified by a public organization, and they are, of course, taking the resources in and investing in order for that software to get built. That costs money. But that work isn't necessarily, the developers doing that software development isn't necessarily being done by people who are employed by that civic organization. Very often what they will do is they will do a procurement, which will allow them to contract in development services to write software to their specification. And so now part of that procurement process is, can it meet the standard for public code? Can it be open source software? Can it be according to the standards of whatever standards are important for their domain? So there's always going to be commercial entities involved. Very rarely do we see something that doesn't have some level of public-private partnership at least. And so one of the things that the support pillar of the Foundation for Public Code can help an organization with is having a market consultation where the public entities sit with the potential market parties that would be available and help them put together what would a procurement look like, so that it's something that meets the needs of the civic organization, and also is something that the vendors say, oh yeah, I can sign up for this. This is describing packages of work I'd be happy to bid on.
Great insights. Thank you a lot. Those were great presentation, a great Q&A. So thank you, Erik Herman.
Thank you.
Now, Dong Zhang with ScaleFlux presents how MariaDB meets solid-state computational storage drives higher performance at lower cost.
It's really my great honor to have this opportunity to share our experience on allowing MariaDB to benefit from the emerging computational storage drive. We know that as CMOS technology scaling is reaching to its limit, the computing infrastructure is transitioning from the traditional CPU-only homogeneous computing towards domain-specific heterogeneous computing, where certain computation tasks migrate from CPU to other computing engines, including the standalone PCIe accelerators, smart network card, and also lately the computational storage drive. Altogether, they complement with the CPU to form a truly heterogeneous computing infrastructure. The basic concept behind the computational storage is very simple. We make each storage drive be capable of performing certain computations on the I/O data path. This will form a highly distributed heterogeneous computing infrastructure that can maximize the computation parallelism with minimal extra data movement and the latency overhead. Our company ScaleFlux has been leading the wave of computational storage drive, and we are the first to launch computational storage drive into the commercial product. And our current product, which is a special class of computational storage drive with built-in transparent compression, has become GA and is being deployed worldwide, mainly in the database application domain. So actually recognizing this grand trend of computational storage, the Storage Industry Association, SNIR, has commissioned a working group in charge of its standardization, where ScaleFlux is a founding member. In the heterogeneous computing landscape, regarding the commercialization of computational storage, data path transparent compression apparently is the first low-hanging fruit to pick. Its basic idea is very simple. Compression is done in hardware on the I/O path, completely transparent to the OS and the user application. Our current product uses a single FPGA to handle both flash control and the per 4K byte Zulip compression. And we implement the flash translation layer in a kernel space driver that exposes the storage drive as a standard block device to the Linux block layer. This cartoon further illustrates its difference from the current practice. On the left-hand side is the current practice where we use either FPGA or accelerator to handle data compression and deploy normal SSD. On the right-hand side, it is a computational storage drive with data path transparent compression. Here, a single FPGA integrates the function of the flash control and the compression. And so by combining the functions, all these functions into a single chip, this drive can fill up the host CPU cycles and minimize the data movement and enables the compression throughput to scale with storage capacity. So this figure compares the compression ratio between our drive and the other popular CPU-based compression libraries like Zulip, ZStandard, and LZ4. We use Canterbury corpus files as a test bench, and each compression chunk size is 8 kilobytes. Because of the storage drive, the 4K byte sector size, the compressed results are 4K byte aligned for all the CPU compression libraries. The results clearly show the high compression efficiency achieved by our hardware-based compression. Now let's see how MariaDB performs when running on the drive with built-in transparent compression. Here, we run 5 different sysbench workloads on both our drive and a competing normal high-end NVMe drive. Even though sysbench generates data with relatively low data compressibility, our drive can still transparently compress the 2 terabyte raw data set with about 1 terabyte, representing 50% of physical storage cost reduction. And this figure compares the TPS of the 5 sysbench workload under 64 client threads. Clearly, the drive with built-in transparent compression consistently outperforms the normal NVMe drive under all the workload. This is mainly because by transparently compressing each page through the hardware engine on the I/O path inside the storage drive, it not only reduces the physical storage cost, but also meanwhile reduce the NAND flash memory chip access contention among all the concurrent I/O requests. This directly leads to higher InnoDB I/O performance. So under high concurrency, like 64 client threads, this further translates into a higher TPS performance. So basically, we can simultaneously gain the storage cost reduction and the TPS performance improvement. Beyond such straightforward usage, we can go one step further to make MariaDB take advantage of the atomic write feature of our drive. So our drive natively ensures the write atomicity for each individual write I/O request from the Linux block layer. Therefore, if each 16 kilobyte InnoDB page can be entirely sealed in one block layer write I/O request, we can guarantee the atomic write for InnoDB and therefore safely disable the double write buffer. So to guarantee each 16K byte InnoDB page entirely stay in one write I/O request, we can first ensure each 16K byte page spans over consecutive or continuous LBA sectors by appropriately configuring the file system. For example, using the big alloc patch on ext4 file system, and then combines with the direct I/O. This can guarantee each 16 kilobyte InnoDB page entirely forced into one write I/O request without demanding any changes to the existing I/O stack. So accordingly, we can leverage the atomic write feature of our drive to safely disable the InnoDB double write buffer. So actually, the latest MariaDB 10.5 already has built-in support to allow users to conveniently use our SkillFlex drive's atomic write feature. The result here shows the performance benefits in terms of both TPS and the 99th percentile of tail latency. So here, the gray bar represents the case of using normal NVMe SSD. The middle purple bar represents the case of using our drive with double write buffer still on. And the orange bar represents the case of using our drive with double write buffer turned off, enabled by the atomic write feature. The results clearly show the write-intensive workload can significantly benefit from our atomic write feature. We can double or even triple the TPS performance and meanwhile reduce the 99th percentile latency by over 60%. All these performance benefits come together with 50% lower storage cost. So as mentioned earlier, the Sysbench dataset has relatively low data compression ratio of only 2:1. So many our database customers report higher or even much higher data compression ratio like a 3:1 and 5:1 on their real data set. The higher data compression ratio is, the better customers can leverage our drive to improve the performance and meanwhile reduce the storage cost. So our drive operates as a standard block device in Linux, and all these benefits come transparently without changing a single line of code in MariaDB, and also without changing the existing I/O stack. So it's very simple, like it's just a plug and play. So beyond this atomic write feature, we can go one more step to rethink the implementation of InnoDB redo log upon the arrival of a computational storage drive with built-in transparent compression. We know that redo log is a very critical component in database, and in current practice, once we write one transaction into the in-memory redo log buffer and commit the transaction, the entire 4K byte block will be flashed from the redo log buffer to one 4K byte sector on storage. And after the compression, transparent compression in our drive, the compressed data block will be stored in NAND flash memory. And later on, once we write another transaction into the in-memory redo log buffer and commit the transaction, the 4K byte block consisting of both current transaction and the previous transaction will be flashed to the same 4K byte sector on storage. Then the compressed data block is stored in NAND flash memory. In the same way, upon committing the third transaction, we will rewrite the same 4K byte sector again and store the compressed data block. As transactions keep accumulating in the redo log buffer, and accordingly we keep writing updated redo log buffer to the same 4K byte sector, the same transaction data are compressed and written to NAND flash memory multiple times. In this example, the same transaction 1 data are compressed and flashed to NAND flash memory by 3 times. So this directly leads to the write amplification. A larger write amplification clearly causes more interference with other I/O requests, and more importantly, it will shorter we will shorten the NAND flash memory lifetime. This will become particularly critical for the emerging upcoming QLC NAND flash memory. So to reduce and even eliminate the write amplification caused by redo log, we propose a sparse redo log data structure. The basic idea is very simple. Instead of tightly accumulating transactions into redo log as in current practice, we always allocate a new 4K byte sector after each transaction commit. For example, when committing the first transaction, we flash the data to the storage. Inside the storage drive, the 4K byte sector is compressed and stored to NAND flash memory, just like in current practice. However, right after committing the first transaction, we put the next transaction in a new 4K byte space and flash it to a new 4K byte sector on the storage drive. So in the same way, for the third transaction, we put it in another 4K byte space and flash it to another new 4K byte sector on the storage drive. Clearly, we waste a lot logical storage space by not tightly accumulating data transactions in redo log. By underutilizing the logical storage space, we eliminate the redo log write amplification. And this can help to improve the overall system storage I/O performance, and more importantly, to improve the NAND flash memory lifetime. So for the purpose of illustration, this figure shows the write volume reduction by replacing the conventional redo log with our proposed sparse redo log. Here we assume that right after each transaction is written to the redo log buffer, we immediately commit and flash to the storage. The horizontal axis is the size of each transaction, ranging from 128 byte per transaction to 2 kilobyte per transaction. So the result shows that the smaller of each transaction is, the more we can reduce the redo log write volume. With 128 byte per transaction, the proposed sparse redo log can reduce the write volume by over 90%. And so this clearly shows the benefit of this sparse redo log. To further leverage the transparent compression, another idea is to modify the InnoDB by deploying the dual in-memory versus on-storage page format. The basic idea, again, is very simple. When a page stays in the buffer pool, it keeps the existing conventional raw-based format. When flashing a page to the storage, we convert it to a column-based format and transform each column to improve the data compressibility so that it can be much better compressed by the computational storage drive with built-in transparent compression. And the raw column page format conversion is handled by the InnoDB background I/O threads, completely transparent to the other modules in MariaDB. So for the purpose of demonstration, we incorporated into InnoDB by only adding 600 lines of code. And our Sysbench-based benchmarking result shows that the proposed dual-mode page format can further reduce the InnoDB storage cost by 50%, and the on-the-fly page format conversion only incurs a few percentage of TPS loss. So this simple idea can provide a very nice option for users to take better advantage of transparent compression. So in conclusion, we show that MariaDB can significantly benefit from the emerging computational storage drive with built-in transparent compression and atomic write to simultaneously improve the performance and reduce storage cost, without changing a single line of code. Moreover, by slightly changing the source code to incorporate the sparse redo log and dual mode page format, MariaDB can take even much better advantage of computational storage drive. So at SkillFlux, we sincerely look forward to best serving the MariaDB users with our computational storage drive. And also, we look forward to working together with the MariaDB community to further explore how MariaDB can take full advantage of such a new storage hardware. So this ends my talk. Thank you very much.
Thank you, Tong Zhang, ScaleFlux, great presentation. And thanks for joining. You're joining from Albany, New York, are you?
Yes, yeah.
Very good. So let's start by the very simple thing, what your product is doing. So this SSD with high compression and fast response time, low latencies. That's sort of in a nutshell what the idea is here.
Yes, just basically we just do the drive will just handle the built-in transparent compression and without consuming any CPU cycles for reducing the data volume.
Right. Yeah, you got a couple of very good questions over Zulip there. We'll return to them. But I'd like to ask first for the efficiency when it comes to data compression ratio. What's a typical, if the idea here is to get good compression, what kind of ratios do you normally achieve?
Yes, so our MariaDB customers actually observed that the compression ratio achieved by our drive typically range between 2:1 and 3:1. That means our drive can transparently reduce that by 2 times to 5 times the data volume.
That's great. So if I want to take that into use, how much configuration and stuff do I need to do to deploy such a thing?
Yeah, that's a very good question. So actually, our drive mount into Linux as a standard block device. So the users do not need to change any single line of code on the MariaDB, on the Linux. The only thing the user need to do is just simply install a driver on Linux. So that's it. We have pre-qualified our driver on all the major Linux distributions and provide RPM package to make the installation is very easy, like just a simple click. That's it.
Good. So then to the question that you got over Zulip, it was a bit into latency and performance and all of those implications of using, of having to do compression and decompression. So how is latency and performance impacted?
Yes. So as I mentioned on the Zulip, like the pure impact on the latency is that really the hardware engine in our drive can handle the compression, decompression in just a few microseconds. So that compared with the flash memory read and write latency of hundreds of microseconds or like a millisecond, that is completely negligible. And moreover, when we run MariaDB, then we will generate a lot of I/O read and write requests. So by transparently compressing the data, actually we reduce the traffic on the flash memory media. So actually that under the heavy stress, heavy workload, we can actually reduce the end-to-end latency.
Yep. So even though you do sort of more work, the reduction of the data will improve or reduce the latency.
Yes, because like really reduce the data will reduce the data confliction inside the flash memory, because we only have a finite number of flash dies. So then if I reduce the data, then we reduce confliction. Then we can more efficiently utilize the flash memory. Then we can achieve higher effective bandwidth. So then we can achieve better throughput and then lower end-to-end latency.
So you keep talking about your storage drive in singular. What about multiple storage drives, several ones? Does it make any sense to have several ones in one server?
Yes, that's also a very good question. So actually, users can seamlessly deploy multiple drives in one server because all the drives carry out transparent compression in fully parallel on their own in hardware. So actually, the more drives we install, we deploy in one server, actually the higher benefit we can gain, the user can enjoy. So really, actually, we encourage users just to deploy as many drives as possible, as you want, and also the installation is also very easy. Just like install many block device in Linux. That's it.
Sounds very good. I think clear presentation and clear answers over the Q&A. So thank you a lot, Dongjiang, for a great presentation.
Sure. Yeah. It's really my great honor to have this opportunity to interact with the MariaDB community. I really look forward to more interactions and serve the community better. Great. Thank you very much.
Our next presenter is Federico Razzoli, Temporal Tables.
Hi, I'm Federico Razzoli, and I'm going to talk about one of the most interesting MariaDB features, which is temporal tables. I am a database consultant. I'm specialized in MariaDB and MySQL, and I have a preference for open source technologies. I recently started this new company called Database. So let's start by taking a quick look at the landscape of temporal tables implementations. As you can see from this slide, they were implemented by all traditional proprietary database systems, which means Oracle, DB2, SQL Server, and also Snowflake, which is proprietary cloud database for analysts. They are also implemented by open source databases, but with limitations. So PostgreSQL has a complete implementation, but it's implemented as an extension. And this extension is not available, for example, in RDS or in Cloud SQL. CockroachDB has a limited but decent implementation. CruxDB, which is a NoSQL database, well, it's actually built around the concepts of bitemporal tables, but it's not an SQL database. The same applies to HBase, which has the concepts of raw versions, but it's no SQL database, so it's something different. And MariaDB implemented temporal tables in version 10.3. Initially, they were only system-timed version, and in the following version 10.4, they implemented application time tables. And you can actually use both these features for the same table, and you get what we call a bitemporal tables. We will see what it means during the rest of the talk. So let's start by application time tables. Application time tables are tables having two special columns. I call them temporal columns, but it's my terminology that I use for clarity, and you will not find it in the documentation or in technical articles I've read before. And basically, the versioning is not automatic. When you insert rows, you take care of registering when the validity of the rows begins and where the validity of the row ends, using these temporal columns, which are basically two timestamps, the beginning and the end of the version. So this is an example that we will use for the rest of the talk. A ticket table, which basically represents some sort of support ticket. There is, of course, a primary key, which is an ID column. There is a state, which could be open, verified, fixed, invalid, and when you create a row, it's typically open. And then there are a summary of the ticket and a longer description. But at some point, we decide that we want to track the changes to the rows of this table. So here's what we can do. So basically, okay, we do it with a normal alter table. I wanted to highlight that this puts a lock on the table, a shared lock. So basically this means that reads on the rows are possible during the operation of this alter table, but writes to the rows are not possible, and basically they are queued. And the algorithm used is copy, which means that MariaDB creates internally a new copy of the table, so this requires more space on disk. This can be a problem if you have small disks and the table is big. Then we create, as mentioned before, the temporal columns. In this case, they are date-time columns, but they could be also date or timestamp if we prefer. And then there is a special syntax, add period for time period is actually the name of the time period. We can specify any name we like, but I suggest to use time period or something equally clear, because this could be used in some of the queries. And if you use XXX, well, the queries will not be very readable. And then we specify the names of the temporal columns. Note that you can use any storage engine for application timed tables. Okay, here I show a problem of creating a table in this way, because basically the first insert in this slide fails. Why? Because we did not specify the values for the temporal columns. Okay, the second insert succeeds because we specify these values. So this is one reason why this is a better way to create an application timetable. So let's see step by step what we are doing and why. So first we create a new empty copy of the table, which we call ticket temp. Then we alter this copy and we start by creating the temporal columns, but the difference is that now we are adding default values. So for the valid from column, the default value is now, so the current timestamp. For the valid to, well, typically when we insert a new row, it's still valid, right? So in this case, the default value is the highest possible value for a timestamp. Then I create two indexes, probably two bad indexes, but my point is please create indexes because you are going to use temporal columns. So as you can see in this talk, I'm specifying not just what you can do, but what, in my opinion, you should or should not do. I think this is probably more important than just explaining a feature, because basically I'm showing you what experience taught me. Okay, so the next step is modifying the primary key. Why? Because if ID is the primary key, we cannot have two rows with the same ID, even if they are valid in different periods of time. We solved this problem by adding valid to the primary key. Okay, so we drop the existing primary key, we add a new primary key with ID and then valid to. Then we populate the table somehow, and then we run rename table. It's important to notice that rename table is an atomic operation. So basically we are switching the names, but in no point in time the ticket table does not exist. Okay, so there is no service disruption. It's also important to notice that the operation we made with primary key should also be made with all unique indexes. Okay. So here I show that if we run a plain select, basically we get not just the current data, but also the rows that are not valid anymore. Okay, this is the default. To avoid this, we add a where clause. I used a syntax I like because I find it more clear, because it's near to what I would say in English. So basically I say where the valid from value is less than now, and the valid to value is higher than now. Okay, so the row is actually valid now. Here I show how to delete rows properly. So we don't really run a delete on an application time table. At least most of the times we will not do this. Instead, we will run an update to change the end of the validity of the row, and we change it from at some point in the future to now. Okay, so from this point on, the row still exists, so we can read it, but it's not valid anymore. So I did this with the store procedure. So here you can see the store procedure in action. We run a plain select, we see the row, we run ticket delete, then we run the select again. The row still exists, but the valid to value changed, and so the row is not valid anymore. So basically, what is the real advantage of creating an application timetable? Well, basically, by doing so, we are then able to use a special syntax that I demonstrated here. So suppose I want to physically delete historical rows, so I'm not preserving the history anymore, because it doesn't matter anymore, right? If our application runs for 20 years, I don't care anymore about what happened 15 years ago. Then I have this special syntax, which is delete from table name for portion of time period name from a certain timestamp to another timestamp. Okay, well, in this case, I also added a where to show that you can do it. But probably most of the times you will not. I suggest that if you do this, the beginning, the start timestamp is always as low as possible. Okay, so it's ideally the beginning of time, because in this way we only delete the oldest data. But if we have data for like starting from the 1999 and ending today, and we decide to delete data from data valid from the year 2000 to the year 2001, well, it is possible that some rows are valid for a longer period of time. So what will happen? Well, these rows are split into two versions. Okay, so there is a version which is older than the period that we are deleting, and a version that is newer than the period we are deleting. And basically, I think this is very, very, very confusing, and we should not do it unless we have very good reasons. The same syntax for portion of also exists for update. Is it useful? Well, yes, it is, because, for example, instead of physically deleting a row, we could mark a row for deletion. So basically, maybe there will be some sort of tool that we read the rows marked for deletions, and it will store them elsewhere outside of MySQL before they can be actually deleted. So let's talk about system versioning. So system version tables. I will use the abbreviation sysver, which is probably only mine. I'm not sure if you can find it in the documentation, but if I say sysver, you know what I'm talking about. Basically, the difference is system version tables are much more automatic. When I insert a row, the beginning of the validity is now. I cannot even change it. When I delete a row, well, yes, I can run delete, but the row is not physically deleted. Instead, an older version of the row is stored. Okay. Well, there is a way to also delete it, but I will not demonstrate it now. So let's back to our example, the ticket table. So this is the original example, so the table is not application timed. So this is the alter table that we can use to make the table system versioned. Again, I wanted to highlight that there is a shared lock and that the used algorithm is copy. And then we simply add the syntax for system versioning. But again, there is a better way to do this, which is basically we create the temporal columns, which I called in this case inserted at and deleted at. These columns are actually also generated columns. Okay, so you can see the syntax generated always as row start or row end. These columns exist anyway, even in the first example. But the difference is if I'm creating them explicitly and I'm deciding their names, I can use them. I can mention them in my queries. Otherwise, I cannot. But anyway, I'm also declaring these columns as invisible, which means if I run a select star, the values of inserted at and deleted at are not returned. Okay, they are only returned if I mention these columns explicitly in my select. You don't have to do this. I'm just recommending to do it, because I think it's more practical. Then there is add period for system time. Then I specify again the names of the temporal columns, and then I specify add system versioning. So the syntax is a bit redundant, but well, you can get used to it. I wanted to highlight you can actually use any storage engine except for Connect, because there is a bug that prevents us to use Connect for system versioned tables, which is probably not super useful, but well, it could have some use cases. So if you're interested, you can follow the bug, because MariaDB has a public Jira. And then there is another bug or feature request, which is support datetime for row start and row end, because SQL standards specify that you can also use datetime. Then I show how to query a sysver table. So what I wanted to highlight is, in the first case, select star from ticket, I get only the current data. I will not get historical data. This is very different from application time tables, right? Then in the second example, I mention explicitly inserted at and deleted at, because I also want to see these values, but I'm still getting only the current data. The third example shows how to get the historical data as well as the current data. And I do this with this syntax from table name, and time all. Okay, it means get all the versions of the rows from this table. Then I show how to get all versions of the rows. Okay, so well, basically I'm showing how to get the rows that were deleted or updated. So the first two syntaxes are special syntaxes that are part of the support for temporal tables. So as you can see, you can add from timestamp to another timestamp or between timestamp and another timestamp. Well, this is shorter maybe, but you have to learn a new syntax, and if you use an ORM, I'm sure that the ORM will not support this syntax. If you use some special tools, they will probably not support or understand this syntax. So I suggest to use actually the third syntax, which is just plain SQL. I add basically where deleted at less than now, so less than current timestamp. Here I show how to get the history of a particular row. So basically I specify again for system time all, and then I specify where ID equals. And also an order by, because otherwise it will be probably a bit confusing. Then I show how to read rows from a specific point in time. So for example, here, the first syntax is actually a special syntax, and it's for system time as of timestamp, and then the timestamp. But again, it's shorter, but I'm sure it's not supported by any tool or ORM or anything. So I prefer to use the plain SQL syntax, which is, well, I do it in a way I personally like, so timestamp between inserted at and deleted at, but it basically just means, if you don't understand it, it means where inserted at less than timestamp and deleted at greater than timestamp. Okay. So here I show that you can use what I call a temporal join. So as you can see, I'm joining a table to itself with two different table aliases, of course, but take a look at the where clause. Basically what I'm actually doing is joining the ticket table at a specific point in time to the ticket table to another specific point in time. So without digging into all the clauses, basically what I'm doing is I'm getting the rows that were present on a certain time, and the state was not changed after 1 month, right? So let's say some words about indexes. Okay, if we are using a sysver table, the row and column is automatically appended to the primary key and to all unique indexes. One thing to notice is you probably know that a query can use a whole index or the leftmost part of an index, so its first columns. So basically this means that if the primary key or a unique index was usable for a query before this change, it will also be used usable after this change. So the change will not affect negatively some queries. This is actually what I suggested to do explicitly for application time tables. And the reason is, if we don't do this explicitly, well, this will not happen at all for application timetables. Okay? So the final part of the talk is just some hints about what you can or should do. So some things you should do are, or you can do, are, well, a table can be both sysverse and application timed. In this case, we will call it a bitemporal table. Okay, so we can query the rows based on their system version validity or based on their logical validity. We can run statistics on the rows that were added or deleted or changed by year, by month, weekday, day, or whatever. We can run statistics on the row's lifetime. We can get the rows that never changed, or we can get the rows that change too often, because maybe this is a bit suspect, so this indicates that there is something strange. And we can also examine the history of a particular row. Why? Because, well, maybe a row we suspect it changed because of an application bug. So we want to check what actually happened to that row over the time, and we can do it. Some more things that we should or should not do. Well, a primary key, first of all, should never change, because otherwise it will become impossible to track the history of rows. If you are not 100% sure about this, maybe you should create a trigger which basically checks if old ID is different than new ID, and if it is different, it throws an error, so the statement fails. For application timetables, you should never do hard deletions or hard updates, because otherwise you will not have old versions of the rows. If you have to drop a column, you can actually move it to a different table, because in this way you will avoid losing the history. And if you have to add a column, and the column is not often read or written, well, you can consider putting it into a different table, because in this way you will not have a new row which doesn't, a new column which doesn't have a history until now. Okay. And if you run statistics or complex queries that involve temporal columns, well, you should probably add a persistent generated column on these temporal columns, and then add indexes on them to make your queries faster. So what we left out, this is not even a complete list of what we left out, but the time is what it is. So first of all, I did not show any SQL for the last two slides because there is no time. I did not mention alter table. Basically, alter table, of course, can delete part of the history or change it, even worse. So alter table for temporal tables is disabled by default, but you can actually enable it. You can use partitions, one or more partitions, to store the history of the rows. Dumps are affected by system version tables. So please check the documentation to find out how it affects dumps. About replication and binary log, again, please check the documentation for possible problems caused by system version tables. But a last hint, suppose you are using MySQL. MySQL does not support temporal tables. Maybe at some point you want to use temporal tables because maybe you want to allow analysts to inspect production data. What you can do is to attach a MariaDB replica to a MySQL primary server. So you replicate data and then you change existing regular tables in MariaDB from what they are now to temporal tables, system version tables. The main problem with this is that if replication lags, of course, the timestamps will not be correct. But maybe you don't care in some cases, so you can actually do it without major problems, in my experience. So thank you for attending. I hope you found this talk useful. As you can see, it was quite opinionated because I really believe that it's important to comment the features and not just explain what you can actually do. Because what you should do is sometimes very different from what you can do. So this is question time. So thank you very much. Please ask your questions.
Thank you, Federico Razzoli, Vetabase, joining in from London. Hi there.
Hi, thank you, Kai. It's great to be here.
Yeah, I saw you not a long while ago, but that was in Paris.
Yes, magic of the virtual events.
Magic. So looking at what you presented about temporal data, I saw sort of three types of temporal data there. Application time tables and system version tables, and then you said a combination of the two bitemporal tables. So how should I pick between these three?
Good question. Basically, system version tables track when the changes actually happened in a table from a physical point of view, while application time tables are about when a row is logically valid. So I can insert it now and declare that it was valid 1 year ago and it's not valid anymore. And a bitemporal table, of course, it's a combination of the two things. So I would say use application time tables when the time is important for your application, and use system version tables when for security or for compliance to some kind of regulation, you need to know exactly who modified what when.
Good. That was a very clear answer. So let's see whether you have equally clear an answer to the following one. So MariaDB isn't alone in having temporal tables of various kinds. Proprietary database management systems have it as well. How would you compare MariaDB's implementation to that of others?
I love this question because there is some kind of idea that open source databases implement the same features as proprietary databases, but not at the same level. But in this specific case, at least, it is exactly the opposite, because if you look at the documentation in SQL Server and in Oracle, the implementation is not as complete as it is in MariaDB. Last time I checked, actually, neither SQL Server or Oracle implemented bitemporal tables. But DB2 does, to be honest, yes.
Cool. So I would imagine that there's a performance implication from using temporal tables. I would be surprised if there were not, but how would you compare the speed, the performance effects between temporal tables and normal ones?
Well, I would say, as I mentioned in the presentation, system version tables have indexes which automatically include the end of the validity of each row, but those indexes are usable by every query that is built without keeping in mind that the table is a temporal table. So as a consequence, for reads, potentially there is absolutely no difference in performance. There could be some small difference in write performance, but I don't expect it to be easily measurable, honestly. So if you need to track the time, please use temporal tables and don't worry too much about performance.
Cool. So then, how does this all relate to archival? So you will archive data anyway, and do you then treat the archival of data differently for temporal tables than for normal tables? We had earlier presentations in Europe, and later on we'll have them in New York as well, about the S3 storage engine. So how does temporal table relate to archive?
Okay, this is also interesting. Well, the thing is, if you define an application timetable, you can actually delete the old rows as you like. So you define your archival strategy without many problems. If you define a system version table, then the table is theoretically read-only. But there is a trick here which I didn't really mention in the presentation, which is a system version tables can be partitioned, and you can use one or more partitions to store the old data. If you do this, it is very simple to delete the history, because you can just drop the oldest partition, and then the oldest data will be deleted. Even if this is not really directly related, MariaDB offers a couple of interesting features for archiving, right? So you can actually move those partitions into new tables, and probably you can use an S3 table to just move that data into Amazon S3 or some other S3 implementation. And this is very good, because in that case, you will still be able to read data if necessary.
Okay, so chatting around about these temporal tables, people have been worried about secondary effects on things like performance or size. Specifically, I got a question about binary logs. I would imagine that it shouldn't influence it, but can you say whether the binary log is influenced by temporal tables, and if so, how and why?
No, it is not, because the history, the older versions of the rows are stored in the table files, not in the binary log.
Right.
So there is no problem here.
Yeah, so the binary log is on the statement level. It's not row-based replication, I suppose. That is the reason.
Yeah, but even if it's row-based replication, you will just have 2 more columns in the binary log, so it's not supposed to be a problem.
Yeah. Did you get any other interesting questions over your Zulip chat?
Let me check.
Well, you don't have much time because time is running out.
Okay. Did you get the chance to actually replicate the data from MySQL, just version it using MariaDB and inspect? Yes, this is something I actually did. So there were these, MySQL production servers, and basically there was this need for data people like analysts to run queries on production data and inspect how the data has changed. Now, migrating to MariaDB for this could be a good idea or not, but in that case, it was simply a bit too complicated. So what we did
Great
was,
answer, by the way. Sorry for having to interrupt you, but we're running out of time. But I will see you again during the rest of the conference. So thank you, Federico Razzoli. Great presentation.
Thank you very much. It was great to be here.
Next up, a core developer of MariaDB Server, Sergey Petrunya, analyze for statements MariaDB's hidden gem.
Hello, my name is Sergey Petrunya. I am a MariaDB developer, and this is a talk titled Analyze for Statements, MariaDB's Hidden Gem. Analyze for Statements is a feature in MariaDB. It is actually not a new feature. It has been introduced as early as in MariaDB 10.1. And I think it got much less recognition than it deserves. That's why the talk is titled Hidden Gem. It was improved in the next MariaDB versions. We improved it based on experience we had with it while diagnosing real-world issues. And finally, in MySQL 8.0.18 last year, there was a feature introduced called Explain Analyze, which is very similar. So I thought it would be a good time to talk about Analyze for Statements again and also compare it with its MySQL counterpart. So the plan of the talk: first we'll look at Analyze in MariaDB. There are two variants of it, Analyze and Analyze from JSON. Then I'll describe Explain Analyze in MySQL, and we will compare the two features. Before we talk about Analyze, let's have some background. What do you do when you got an optimizer problem? The first thing to check is to look at the Explain. Explain shows the query plan, and sometimes the problem is immediately apparent from the Explain. Like, for example, Explain may show you full table scan, and you know your query shouldn't be scanning all rows in the table. In other cases, the problem is not as apparent. One of the things that you don't really know whether query plan matches the reality. The plan has numbers of rows that the user expected to read, and numbers of fractions which would expect to pass the where condition. We don't know whether that matches the reality. And the second crucial thing it doesn't show where the query would be actually spending its time. Like here it is not clear which of the tables will take more time to read. Is it scanning all of this table, or is it making index lookups into line item table? Enter Analyze. If we compare it with Explain, Explain optimizes the query, and after the optimizer finishes, it prints the Explain output and finishes it. Analyze also optimizes the query. Then it actually runs the query. While running the query, it discards the query output, but it collects execution statistics. And then it produces output that's very similar to Explain, but annotated with the statistics collected during execution. Let's take a look how it looks like. Here we run Analyze, select, and then there is a join. We are looking for all orders made between these two dates, and then those that have items in these orders which have price greater than 1 million. We see that in Analyze output there are two extra columns. R rows and R filtered. R stands for real. That is, R rows is how many rows were actually enumerated in that table, and R filtered is what was the observed condition selectivity. If you look at R rows, for full table scan or full index scan, these are typically close to the expectation. The expectation about how many rows in the table is precise, although they can be very different in case of limit or subqueries, where the optimizer will cut the query execution short. For range access or index merge, the other range-based access, it depends on the storage engine. Within a DB, you can expect up to 2x difference. You can have a bigger difference in edge cases, in which case basically the workaround is to ignore index. The most interesting rows is when the type is ref. It is ref is making index lookups based on the lookup value constructed from previous table. Like here, for each order, we make a lookup and we expect that there are two items in the order. What we have observed, actually, we saw that there are on average 4 items in the order. Since this is average, some amount of discrepancy is normal. But sometimes the discrepancy can get very large, tens, hundreds of thousands, and then it's worth investigating. For example, an important special case is when rows equals 1, while real rows is much greater. That means you don't have index statistics and you should rerun analyze table. If you see there is a huge discrepancy, it's worth rerunning analyze table as well. Then if the column has lots of null values, by lots I mean more than half of the rows have nulls, it's worth looking at in the dbstats method. Otherwise, if the column has very skewed data distribution, like most orders have only a few items, but there are also some really huge orders, well, then the situation is complex. One advice would be that if an index cannot produce reliably good query plans for you, you should consider ignoring it. The second important column is R filtered. R filtered is selectivity of using where, how it is a fraction of rows which will be left after using where here applied. And here we see that using that after table line item R filtered is 0, that is no rows passed this condition. And if you see R filtered is much smaller than 100, that means the query is reading and discarding lots of rows. The first rule to do is that check if conditions in the where clause are in the form that allows index use. You can use explain or analyze format JSON to see what the condition is attached here. Look at consider indexes. We could here add an index on extended price if this is if you are very frequent to have queries querying on price. However, one should not change filter at 100%. Because there is always a trade-off between reads and writes. Adding extra indexes has extra cost. They slow down updates, they make your database larger, and make the optimizer job more complex. One other angle that you need to know about R filtered is that since filtered it shows how many rows will be removed from consideration, it is very important value for end-way join optimization because it shows how many rows, how many times the second table will be accessed. So if you see R filtered and filtered being very far apart, typically it will be R filtered much smaller than filtered. This shows that the optimizer has a wrong idea about condition selectivity and it might be producing poor query plans. And if you can't afford adding an index, consider at least collecting a histogram so that optimizer knows that in this case that condition on L extended price is going to be very selective. Summary for analyze, there are 2 new columns, real rows and real filtered, which allows you to check the estimates with reality. Now let's move to analyze format JSON. Analyze format JSON is explain format JSON meets analyze. The syntax is analyze format JSON, and if you look at the basic query, like here we see it produces JSON output. It's similar to explain format JSON output, but it also has extra members, quite a few. In blue you see there are real rows and R filtered, which we are already familiar with. And there are also more marked with yellow. R loops is number of times the operation was executed. Here the query was executed once and the table was scanned once, so R loops is 1. Then there is R time ms. R total time ms is total number of time the query took, so 190 milliseconds, of which 142 milliseconds were spent reading from the table orders, and 48 other milliseconds were spent called other time, that's checking the where together with other auxiliary info. There is no further breakdown because taking time measurements too frequently has an overhead. So there is a limit about how often we can note the time. Let's try a more complex query. Let's get back to the join we had a few slides ago. Again, line item and orders. Here we see that there is a query block. It's got R loops and R total time ms, 4 seconds in total this query took. Then if you look at table orders, it was read one time. It took 300 milliseconds. So it was a full table scan, but it wasn't the worst thing about this query. And if you look about line item, we see that only 4 rows were read each time, but it was done. The table was accessed 1.5 million times. So in total, reading from the table took 3.5 seconds. And this is the lion's share of the query time. Checking the where and other auxiliary took 150 milliseconds, so it's probably not okay. Now one could say that you could guess that from this query, but for complex query with selective where condition, its R loops is really useful, and R total time ms allows you to instantly see where the time was spent. Let's try it with the subquery also. Here is the subquery. We find orders on these dates such that the sum of this order is 90% of what the user has ordered in total. So user's biggest order. Each subquery has an R query block entry which has R total time ms. So here we see that the mine select took about 1 second and the subquery took also, so the time was split between these two nearly equally. Again, when you get a large query with lots of subqueries, it's really helpful because there are subqueries which don't look as heavy like this one. It reads just 7 rows, but it is executed multiple times, so it adds up. On the other hand, there can be subquery which takes some time, but it only executes a few times. By the way, here we can also see that the expression cache was used for the subquery. It got about 200 hits, had a hit ratio 0, after which it has disabled itself because it was not helpful for this query. Let's look at some other operations, for example, sorting. Explain in MySQL and MariaDB shows using file sort, which may sound too scary for some people because they think that we're going to actually read files. The second frequently asked question is, what sort buffer size should I have? Is my setting large enough? The third question, those who read there is a priority queue optimization in recent MariaDB and MySQL versions, and it is not shown and explained, so you cannot really easily see whether it was used. You can see it from the counters, but counters don't show it really does multiple sorts, whether some of them are doing it or not. So here we can see that for query with limit, we find 50 customers of greatest balance. We see that the query used priority queue, so it wasn't reading or writing any files. If we search for the top 50,000 customer, the picture is different. Priority queue was not used, but we managed to do one sort pass. Buffer size was 2 meg, and the data fit apparently into one pass. That's very useful. Analyze works for any statement that explain works for, so you can run analyze update and analyze delete. You should, however, be cautious because analyze update will actually do the update and analyze delete will actually do the delete. Here we follow PostgreSQL explain analyze feature, and I think that is the right way to do it because analyze should be as close to real query execution as possible. If you don't want analyze to make modifications, you can wrap it in begin rollback, wrap it in a transaction, and that way this is a way to avoid making the changes. One important question is the overhead of analyze. Analyze data there are two kinds. First of them is counters, how many rows were read. These are cheap to collect, and actually MariaDB will always count them. And then there are time measurements. Time measurements are expensive to make, especially when you need to have many of them. When we're reading rows for table, we basically measure the time each row read took. But maximum overhead that I was able to observe was 10%, and that was on an artificial example that I have constructed specifically to maximize the overhead with very small rows, very small tables, but doing many reads. Typically, the overhead will be less than 10%. Analyze and the slow query lock. I guess experienced DBAs here know that MariaDB and MySQL have a slow query lock, which writes slow queries. And you can also say in MariaDB log slow verbosity explain, which would which should say it's writing explain output into the slow query log, but actually it's writing analyze output. You can see R rows and R filtered. So this way, if the query is slow, you will get its analyze in the slow query log. One would say that analyze format JSON would be nicer. Yes, it would be. There are two obstacles towards printing it. First, that there is no timing data, because as I said on the previous slide, analyze format JSON, so analyze has some runtime overhead. We didn't want it to be always on. So by the time we decide that the query was slow and should go into the slow query log, we already have run it and we haven't collected the timing. Another obstacle is that most common use for slow query log is to run it with parse it with PT query digest, and I'm not sure how to print JSON here in a form that's usable but without interfering with ability of PT query digest to parse it. So, summary for analyze format JSON. It is explain format JSON execution data, R rows, are filtered, R total time MS, and R loops are members that are useful to narrow down problems. Sorting, buffering, subquery caches also report R values about their execution. Please do attach analyze format JSON output when asking for optimizer help or reporting the issue. Will save one round trip. Now let's look at MySQL 8. MySQL 8 got explain analyze feature in MySQL 8.0.18, which was in October 2019. They had fixes and bugs in it and fixed it in subsequent releases. But now I think it's stabilized. It produces a PostgreSQL-like output. It's shown below, so it's a tree-like structure. In the next slides, I will be editing it for greater readability. The reason it produces PostgreSQL-like output is that it has switched to so-called iterator interface runtime under the hood, and after you do that, one can implement, explain, analyze in Postgres-like way very easily. So the basics, let's run explain analyze for one query. We see that it shows query plan basically with costs and expected number of rows, and it shows this actual time rows and loops. Loops is like MariaDB are loops, how many times separation was done. Rows is the number of rows in the output. So if you want R filtered, you get the rows produced by the range scan here and divided by the rows it would left after filtering. And that you compute R filtered. Actual time shows two values. The first is the time to get the first tuple, and the second is time to get all output. They're not total time MS because if the node was executed multiple times, these will be averages. But R total time MS is basically this multiplied by this. Let's look at the more complex query. Here you can see the MySQL's output on the left and MariaDB's output on the right. You can compute R total time MS by taking the second value from actual time and multiplying it by loops. So the usage will require some arithmetic practice, but you can get the same value, yes. For sorting, they show the limit. Here I run again two queries which we ran previously with MariaDB. We show that there is different limit, but it doesn't show whether the priority queue was used or what was the buffer size. It's interesting that specifically for sorting, you can get this information from the optimizer trace. If I run the query with limit 50 and optimizer trace on, I see that file sort priority queue optimization is chosen. And with 50k, I see that it's not chosen and there is a peak memory used. Update delete. If one attempts to run update delete, you will get this error. Apparently, single table update and delete statement are not using the iterator interface yet in MySQL, so explain analyze doesn't work for them. Multi-table update works, and unlike in MariaDB or PostgreSQL, it won't make any changes. So summary, the syntax is explain analyze, Postgres-like output. Unfortunately, not all plant details are shown. Some are in the optimizer trace for some reason. Not all kinds of statements are supported. It can have higher overhead. If I retry artificially bad example, I get about 50% overhead. As far as my guess about why it happens is that they are doing many more timings, taking more timings, and that has more overhead. They show some info that MariaDB does not show. They show time to get the first row, which you don't have in MariaDB. They show number of rows output for each node, and they have nodes for grouping operations. I think nodes for grouping operations would be nice to have for MariaDB. Number of rows output for each node, we need to check this out. Time to get the first row, it might be useful for cursors or other special cases. I'm not convinced that it's worth printing all the time. Let's make a final conclusion. MariaDB has analyze statement, analyze from a JSON. It is a stable feature, very useful in diagnostic optimizer issues. MySQL now has got explain analyze. It's a similar feature, but it has a different interface. Data is different and printed in a different format. There are some things it has that MariaDB doesn't have, but so far I don't see any obvious advantages. If you think otherwise, feel free to file issues or feature requests and we will fix it in the next version. Thanks for your attention.
Thank you, Sergei Petrunya, joining in from St. Petersburg, Russia. Hi there, Sergei.
Hi, Kai. Glad to be here.
So you gave the same presentation now as you did yesterday. How does it feel differently the second time you're presenting it?
Well,
that was a trick question.
Feels good anyway.
It's sort of a hot standby thingy with the same thing being played a second time. So seriously, looking at analyze, people ask when I chat about analyze and optimization and stuff, performance schema often pops up. So they are different, this analyze and performance schema. Would you, briefly in a nutshell, say what's the relationship between analyze and performance schema?
Yeah, well, analyze is about analyzing the details about how one query was executed, how different parts of it, different sorts, joins, how they perform it. Performance schema is primarily geared at collecting system-wide statistics, where you would track your total memory usage, total I/O, and so forth. One can collect like the data that's a bit similar to analyzing performance schema by taking individual events and reconstructing it, but it doesn't have all the information. It's very difficult to map and explain. I had to use that on some occasions before we had analysis support cases, and it was really complicated and hard and required a lot of assumptions. While I think analysis is so much easier that you can literally see where the issue is immediately, and it is basically annotated, explained, so you don't need to carefully map like, okay, how this I/O maps to the query that I'm using. Particularly with self-join, analyze will show you table 1, table 2. They will see which of the join, which instance of the table, which of the reference of the table is you spending time on. Well, with performance schema, you will just see one table, and it's hit many times. And if it is a self-join, it's not possible to tell whether it's accessing the first table or as the second. Yeah.
So analysis for one specific query, and the performance schema is how the server feels overall.
Yes.
So what about a borderline between those, like RAM memory? Usually the RAM memory used is on the level of how the server feels on the whole, but can you also get to know how much RAM memory an individual query is using through analyze?
Well, you can go through all of the nodes and add up the total amount. We don't have the total amount printed. That might be an interesting feature request to sum up and see, and print that also. And there's also the thing that the query may allocate memory, then free this, then allocate another buffer, and it's difficult to say whether you count that as which is the total maximum of the sum of the two. Yeah. So, well, with analyze, you will still be able to clearly see which operations were using the memory, and you will have to compute the sum yourself, but hopefully that's not as painful.
That should be doable. So I was chatting with a MariaDB user who read up about the MySQL equivalent here, and they had a statistic about how long it took to find the first row. And I didn't really understand why would one want to know specifically how long it took to fetch the first row. Do you think it makes sense? And what's your take on this?
Well, time to get the first row is very relevant first when you get like order by limit queries with small limit. And you get query plans which are startup heavy, which typical like bigger databases like PostgreSQL or Oracle more heavily used with hash join, for example, where they have a lot of startup work to be done. And the second thing is that cursors, if you are heavy storage procedure users, some of these open cursors where they just start and read a few rows from it. But it's, I think, has much less relevance for MariaDB or MySQL for that matter, because there is the use cases for MariaDB or for MySQL are not do not typically heavily rely on these heavy storage procedure cursors, and I don't think there is. The optimizers in either database is very advanced in regards to order by limit. We have a task in progress on that, by the way, but it's not finished yet. So my guess would be that MySQL was just following, say, PostgreSQL's example there, because I don't see how that info would be immediately useful right now. Time to get.
So my hunch that it doesn't really make much sense. You sort of confirm that. On the
if it does make sense, I would like to see counterexample. Sorry.
Yeah. So on the Zulip chat, did you get any interesting questions there that you would want to highlight?
Well, there was a question about the slides that there were two queries using order by, and the one on the left was using priority queue and the one on the right wasn't. Well, what's the difference? The difference was a higher limit value. For the query on the left, the limit was very low, I think like 50 rows, which would fit into the sort buffer that was the optimizers allowed to use for sorting. While on the right, it was like 50K or 500K, some value which I picked to not intentionally to not, so that all rows will not fit into the sort buffer, and so the optimizer would pick not to use the file, not to use the priority queue and do regular sorting instead.
Okay. I have a detailed question for you. It's a very, it could be theoretically answered with a yes or a no. You don't have much more time than a yes or a no. GUI viewers, would it make sense to have a GUI viewer? Is there a GUI viewer for the output of analyze?
Currently, no, and I think this is a good low-hanging fruit. Something web-based where one could paste analyze output and see it presented in graphical form would be something that I would even use. But well, it's not planned, so if somebody is able to do so and willing, it will be really welcome addition.
So a good thing to contribute if somebody wants to create a GUI viewer for analyze output. Sergey, Petrunya, excellent work. Thank you, and see you again soon on this conference.
Yeah, thank you too.
Our next presenter, Valery Kravchuk, MariaDB 10.5 new features for troubleshooting.
Hi, my name is Valery Kravchuk. I work for MariaDB Corporation as a principal support engineer, and today I'm going to present you a few details about new MariaDB 10.5 features related to troubleshooting. I'm presenting this from a small town of Vyshgorod, near the capital of Ukraine, Kyiv. I work in MariaDB and MySQL support for more than 15 years already. And in recent years, I'm also a community person, a public person with a blog, a lot of MySQL and MariaDB details published on my Facebook page, with a Twitter account devoted mostly to MySQL bugs. Before that, I was a trainer and consultant working mostly with Oracle databases, so it gives me some Oracle background that is related to today's talk, and I've worked out a habit of creating a simple and clear presentations that can be also used as a reference. So whenever you see an underlined item in my presentation, you can click on it and get a lot of useful and way more interesting information than in presentation itself. I think so. So it's a reference. I should say that I work as an independent consultant. I'm not a marketing person for MariaDB Corporation, so all the views and ideas in my presentations and writings in public are my own, and I do not speak for MariaDB Corporation in any way. This session is devoted to the new 10.5 features in three main areas. First of all, finally, we got more or less incorporated all the instruments and ideas from MySQL 5.7 performance scheme. So performance schema became way more useful. Then we also added some tables to the information schema to make the internal workings of the yet another killer MariaDB feature, namely thread pool, more visible to the end users and DBAs. And there was also a small improvement in the analyze statement that allows to present the way query was executed with details about rows and time spent. So a bit more details are included now. Most important is surely the performance schema improvements that all our users are waiting for several major releases already. To understand how large was this change, we can compare the number of tables in performance schema. That was 52 in the previous release, comparing to 87 in MySQL 5.7 and 80 in MariaDB 10.5. Few tables are still missing, and these tables are mostly related to the group replication feature that we do not have in MariaDB. If we speak about the related variables, we are now having the same number, 42 variables that allows us to set something related to performance schema. If you ever read the new features of MariaDB 10.5 knowledge base page, you will probably noted a section what's new in performance schema that refers to the tasks that were implemented by dev numbers. You can surely click on each and every of these numbers to see what was implemented, but the details there in public tasks are quite limited, so it's not really that much useful. So we will just use it as a reference of what additional details are now instrumented. So we have additional memory instrumentation, metadata logs instrumentation, prepared statement instrumentation. We instrumented status variables at global and server levels, added some instrumentation for storage procedures, added some instruments for SX shared exclusive logs, locking primitive widely used in InnoDB, some instrumentations for transactions, and the last but not the least, for me specifically, is the way to get the values of user variables in user sessions. Previously, one had to apply tricks like reading the internal structures with GDB that I personally had to do. So I really appreciate this addition. A couple of things are not clearly documented, and of them we have several replication-related tables in the performance schema. It's work in progress. It's not yet completed for 10.5. And one important thing for all of you to note is, unlike previously in 10.5 and in MySQL 5.7 and newer versions, we have one important change in the way performance schema works. Previously, it had allocated the memory at startup. So whenever memory grows at runtime, you could be sure that performance schema is not a part of this leak or supposed leak, whatever is it. It's no longer the case. In MariaDB 10.5, some memory to the performance schema instruments is allocated dynamically depending on the load, number of connections, number of tables opened, and things like that. So it's important detail that I wanted to highlight. This highlight actually goes to one of my blog posts where I studied this and presented. So to summarize, instruments, performance schema still controlled in the same way as before. If you want to instrument something, you have to enable specific instruments, and you do that through the performance schema setup instruments table. So we have additionally, just for memory instrumentation, added 270 instruments starting with memory. That's cool. They cannot be timed, but they should be enabled. Some are enabled, some are not enabled. Important thing about the instruments is, and it's presented in my blog post, that some of these instruments are not enabled at startup. And even though they are dynamic, unfortunately, some of them can be enabled only at startup. Think about the InnoDB thread pool. So the huge memory allocation for a thread pool. So to see it in the performance schema tables, you have to add in your CNF file the appropriate enablement. So all that you can see, it's just a small detail. It's common for MySQL and MariaDB as well. So besides the instrument, these additional memory allocations are represented in 5 additional tables that were added. You can see the structure in the MariaDB knowledge base, and we will study one of the tables. Memory summary global by event name. So for each event representing specific place where the memory is allocated, there are a lot of details presented. Additionally, in other 4 tables, we have this split or detailed for example, for a specific user and host in memory summary by account by event name. So account is represented by a pair of user hosts as it's normal in MySQL and MariaDB. You have a summary by host, so different users from the same client host may be checked for the memory usage. And you have a summary table per thread. So you can find out which thread, which user thread uses most of the memory or allocated a lot of memory in specific area. To find out the real MySQL connection ID that you are interested in, you have to join this to performance schema threads table, and you have to join with thread ID column, and there you can find out process ID for the related thread. So that's all interesting. These are additional fields. Let's check on the main fields. Main fields for each memory event are event name, surely, number of allocations, number of allocations, number of attempts to free the allocated memory of this kind, total number of bytes allocated, total number of bytes freed, and current number of bytes used. So the first two is related to the later of those highlighted. So total allocated minus bytes free is current number of bytes used. You have also high and low allocations historically, so you can see what was the largest allocation for this specific event. I also suggest you, really suggest you to check MySQL 5.7 manual, which is very detailed and have a lot of examples of this stuff. We can easily check memory allocations. It's a typical query, for example, find out which memory event, which kind of memory was allocated most often, for example. So top with limit 1, we have a top memory allocator. Where I've got this information from? Actually, it's a test that we should probably check. So I've set up for several examples in this talk. I've set up a simple sysbench test. It's LTP read-only that does some point selects, range selects, and whatever. So when it runs, it generates some load, and then in another terminal, I can check the result of this load. So if I look for memory, I can see, just sorry about that, I should add performance schema here. And we can see that top allocation, that's what was in my presentation, was actually for quick range select, so somewhere in the optimizer. You can see that current number of bytes used is really small, but total number of allocations was quite high because we have a high concurrency. Another next one in top allocations is some memory pool inside InnoDB, and I would like to highlight these interesting numbers here. You are not supposed to see negative numbers here, but you do. It's a known and open bugs in MySQL as well. So along with the feature that we ported, we inherited some bugs. Don't be surprised. If you're interested in the chat, I will show you these bug numbers so you can monitor them for further solutions. To summarize, the internals of the memory instrumentation are different. There is a discussion here in my blog with a key developer, Vladislav Weintraub of MariaDB Corporation, who explained what is the internal difference. Supposedly, our instrumentation of memory is more efficient. I highlight once again the important detail that memory now may be allocated dynamically. So performance schema is a source of kind of memory leaks. And surely we can see a lot of other details. I've demonstrated a bit different queries, so feel free to check different queries. Follow my blog post, I explain all this stuff there. Let's move on. Another additional instrumentation is devoted to metadata logs. We have a metadata logging for plugin historically in MariaDB for quite some time. But in some cases, it's useful to be able to see the metadata logs info in the way performance schema presents. It's easier, it's always there, and it's easier to join if it's all in the same performance schema if possible. So there is only one table, metadata logs, single instrument like metadata, nothing fancy. You will see metadata logs for sure whenever anything runs. So just by selecting from the metadata logs. What about now? Now we have a lot of metadata logs, and surely it's tables from sysbench test. So sorry about that. It's all written on the slide, but I'm too lazy to just copy paste. So important thing here is also that you, if you want to find out which user connection had set the metadata log, you have to join to performance schema threads thread ID table and check process list ID there. So I will not go into the details of what kinds of metadata logs exist. It's nothing new was really added in 10.5 in this regard. Now, speaking about the performance schema, yet another area that we lack before for the visibility is prepared statements. Sysbench uses prepared statements. So now we can actually enable instrumentation. There are several instruments for both server-side prepared statements, like prepare and execute, and for API prepared statements, so-called binary protocol prepared statements, which are MySQL STMT, some C functions in C or other connectors. So there is a single table for prepared statements. So if we check it, we can select count. Surely you will see only active prepared statements there. So now you see 0 once again. That's because the test had completed. As soon as it starts back, we can see that sysbench does use prepared statements for its activity. So here for this session, I enabled and set allowed to measure time for all kinds of prepared statements. There is one addition in MariaDB related to the feature that just does not exist in MySQL. It's execute immediate. So when you prepare statement in place from the string in one step and execute it. So that's additional instrument comparing to MySQL. So we see it works really. We can see what's there indeed if we just do this limit one while the test works. We can see there is some prepared statement. It's not even commit as in my case that I captured for the slides, but it's a real select of a kind that sysbench often uses. So it's cool. Now status variables. It's the same that you can see with show global status, but when they are presented in the relational table, you can apply all power of SQL at the server side, not in your applications. Several tables were added, 8 in total. 3 of them are more or less unique to MariaDB. So we have just performance schema global status with current global status. We have performance schema session status for current requesting session. But what's more interesting, we also have access to status variables for specific thread. It's not unique, surely, but also for the account, for the user, and for the host. So we can like summarize how many read operations all users from specific hosts had executed. It's really cool. Yet another thing is storage procedures instrumentation. I suggest you to read and follow this work log from MySQL. The most detailed description. I cannot find anything similar in MariaDB knowledge base. So if you are not up to reading the code and all the tests and everything for specifications, just read the work log to get the general idea. So previously, there was only kind of object type that was instrumented. It's a table. View surely is also considered a table. With this change in 10.5, we added 4 more things instrumented, specifically functions, procedures, triggers, and events, stored procedures. All of them are, by default, you have to do nothing, are enabled and timed in all databases but system databases, MySQL, information schema, and performance schema itself. So you have to do nothing. You can just check everything. The statement to check is a bit non-obvious for somebody. For the events, you have to check statement scheduler instrument. All the other instruments, and there are many, are called statement SP, stored procedure. And you will not find your familiar commands, typical stored procedure commands inside. They're kind of abbreviated. So there are jumps, return, set, and everything, but not literal statements that you may be used to. Still, you can set all this instrumented, and then you can see how it works. Additionally, it's all timed, it's all included in all the summary tables. There is one additional table created, event statement summary by program. So for specific stored program call, we summarize all the times and number of calls for the specific events. As for a quick demo, I have here, that's why I had test, a small procedure called P1, very creative as usual. Sorry, I missed D. So that's it. It's a typical MariaDB stored procedure. It was created in Oracle mode, and you can see that we use, for example, implicit cursor and cursor for loop. It's cool stuff. So the procedure does nothing fancy really. You can just call it without arguments. It selects usernames from MySQL user table. But what's more important, that you can check the table now, event statement summary by program. So you can see, sorry, we have better to switch to performance schema. Yes, statement summary by program. So if we can check this, we can see that, for example, the procedure P1 was called 3 times, and here how much time in picoseconds was spent executing statements inside. It's nothing special. Call was instrumented previously, but now you can split it into the individual statements and get all the details. This is really a cool part that's yet to be presented in details. Another thing, so-called shared exclusive locks. These locks are used by the InnoDB implementation a lot, and we now have them instrumented. It's internal serialization primitive. It's interesting to check the instruments with name like SX lock actually. Set up instruments where name like %. You will see some famous stuff here. So these are locks, internal InnoDB locks that every DBA and many developers should know, like dict operation lock for dictionary, dict table stats for InnoDB persistent statistics, transaction purge ledge, BTR search ledge. All that stuff is quite important, and you often see it. Now it can be instrumented in detail, so you can see how much time in summary was spent on this stuff. So as for transactions, it's quite simple. There are 3 tables summarizing transactions. Current history, history long, related consumers should be explicitly enabled as well. What's more interesting is that now in MariaDB 10.5 we have 4 levels of hierarchy of events. So we have transactions consisting of statements. Statements are executed in stages, and each stage may have to wait for several events or specific waits. I will not show the demo now because I'm a bit out of time. I hope to present a link to the blog post while this session is going live in comments. The last but not the least is user variables. So there is a single table, user variables by thread, and you can see which user variables are defined in each thread and what is the value. It's easy. Let's just define a user variable and then select from user by thread. That's it. We have a that's from some of my previous tests. We have a variable named a with the value 1. Now go find out this without GDB from any previous version of MariaDB. It's really impossible. So that's the example. It's quite simple. Now, speaking about the replication instrumentation, replication was also additionally instrumented. Related tables are just 4 out of 8, as far as I remember, in MySQL. They are only partially documented in the knowledge base. There is still work in progress because one of the important tables is missing. We have replication applier configuration, applier status, but we do not have a coordinator status. And if we speak about parallel replication, we have a replication coordinator thread and replication applier threads, maybe more than one. So all this should be documented and implemented one day. Probably it will be in 10.6. So speaking about the thread pool, for thread pool, we have 3 tables added. As far as I remember, in the information schema. So here we have to go information schema. And here desk, sorry about that, thread pool. Okay, I made a typo again. So that's it. We have thread pool QEs, we have thread pool groups. Moreover, well, I had not personally used it in real life yet, so I'm a bit slow trying to understand and explain at the same time what is it about. Another important addition is that there are also 2 additional variables. It's not clearly documented in the what's new. So now you have a way to create a dedicated listener thread per group and not be blocked by long-running queries. And to control the content of these 2 additional tables, there is also additional variable thread pool exec stats. When it's set, you have more precise information here. So the only useful reading that I was able to find out so far about this is the following commit that I linked here, so go for it. Finally, the analyze statement. I will not go into much details here. Thing is, now we have 2 measures of time spent. The table access time is reported separately, comparing to the time spent on checking the rows from the table, processing where clause for the table. So now time sums up nicely in the analyze statement for sub-stages, let's put it that way. To summarize, MariaDB added a lot of useful features for troubleshooting, mostly in the area of performance schema. For those using thread pool, and it should be all of us with many connections, there are also a lot of additional details visible in the information schema. Unfortunately, not all this stuff is documented, so I'm going to do it in my blog posts, and I hope it will be done in knowledge base as well. So it's work in progress, even though two minor releases of MariaDB 10.5 already happened. Thank you very much for attention. We are a bit out of time. My last word, as usual in all my presentations, is the following. Please report any issues, documentations, code bugs, your problems that you suspect may be a result of a bug in our public bugs database, jira-mariadb.org. Do as my wife did when she noted a nice bug. Just make a photo, make a snapshot of data, present it, and help us to make MariaDB better together.
Valery Kravchuk, great job. Thank you. You're today joining us from Vyshgorod, close to Kiev in the Ukraine, are you?
Hi. I'm really sorry that my camera is making problems for all of us again, but I hope sound works this time.
Sound works very much, so that's great. Yesterday in Paris, we had to use two proxies for you. First, we changed to Trabario and then Monty. How did they do?
Well, they did well. I think they had fun, and I hope viewers had fun, and they've got some insights on how things are done inside MariaDB.
So what do you think of the format of all of this with hot backups and with the pre-recording thing and all of this?
Well, based on my example, we see that pre-recording was a great idea, because if it fails alive during my session in the middle as it happened, that would be a disaster. So you would end up only with slides and maybe chat. This way you have a talk. Maybe it's not the ideal presentation, but it's the best I think we had seen so far.
It was a graceful degradation, I think, and it saved a lot of our heart and pulse and all of that. It was great for health purposes as well, I can tell you.
I can imagine. It helped me too, really. Otherwise, it would be a really bad failure.
So going now to your troubleshooting, not videos and the presentations, but troubleshooting MariaDB and the new features related to troubleshooting. What are your favorite ones among those?
Well, I would name two. One is obvious because I spent a lot of time during the presentation on it. It's memory instrumentation through performance schema. I was waiting for it for years because the alternative ways to trace memory leaks or potential memory leaks in production are either hardly applicable in general, like any heap profilers that slow down things a lot, or maybe also with bad performance impact, but also hard to implement, like any kind of dynamic tracing of memory allocations, non-trivial ones, would be really non-trivial to implement. So you can use some pre-built tools, you can add probes, and I did that. But just running a set of SQL queries for the data that are always there as soon as you enable performance schema, that's great addition. It's still work in progress because, as I mentioned, there are some obvious bugs in the implementation, but overall, based on MySQL experience with this feature as well, it proved quite useful. And another thing is very MariaDB specific, and it happened and added to 10.5 exactly based on the previous experience with attempts to solve real-life problems. It's additional 4 tables in the information schema that Vladislav Weintraub added to present some internal workings of the thread pool. That is both unique, quite useful, and was really hard to troubleshoot in one specific case until we got down to the stack traces in hanging situation. Now we have an option to find out what's going on inside the thread pool, again with simple SQL queries. I am yet to see this applied to real life situation, because in most cases thread pool just works, you know. So it rarely happens, but it's a great addition, and I am going to test it more and blog about it in details. So it was just a slide in presentation, but the feature is really great. So that's 2 main features from my point of view.
Cool. So I was trying to ask yesterday also from Vincenzo, but he's not exposed to this. You are. So do you have any war stories from how these features have saved you, saving the issues at client cases? And you have about 40 seconds to give a short war story if you have one on store.
Well, so far performance schema, unfortunately, that's true, and I mentioned it, had presented some insights, but they were mostly trivial, unfortunately. In complicated cases, I had to apply dynamic tracing techniques and perf profiler, and that's what my next talk is about.
Yes.
So we have more hopes now with more advanced performance schema in MariaDB, but so far real war stories lead me to dynamic tracing on Linux.
So, and that's, as you said, your next presentation. Very much looking forward to it. I saw a pre-version of it, so let's listen to you for another hour and then get back to some further follow-up questions. But thank you so far, Valery Kravchuk.
Thank you for help. Let's talk about.
Our next presentation is by Valery Kravchuk, Dynamic Tracing of MariaDB Server on Linux, Problems and Solutions.
Hi there. My name is Valery Kravchuk and I'm a Principal Support Engineer in MariaDB Corporation. Today, even tonight, I'm going to present you a talk about dynamic tracing on Linux, in this case applied to MariaDB Server, mostly 10.5 and 10.3. In some examples, I present this from a small town of Vyshgorod, located near the capital of Ukraine, Kyiv. I work in support of MySQL and related products for more than 15 years already. Of them, last 4.5 years in MariaDB Corporation. Since I quit Oracle in 2012, I'm also a community member, a public person who writes about MySQL and MariaDB and speaks at various conferences. I write about MySQL and MariaDB in my blog, on Twitter, even on Facebook. I abuse all kinds of media, and I was eventually noted for this activity last year and got even an award for my bugs marketing and other writings. Before doing MySQL support, I was a trainer and a consultant working mostly with Oracle databases, and from that time I've got a habit of creating a clear, simple, useful presentations full of external links. So whenever in any of my presentation you see underlined text, it's clickable and it will bring you some new document that may be way more useful than presentation itself. Even though I work on MariaDB Corporation, in all my public writings and presentation, I speak only for myself. So a standard disclaimer of a kind is presented. My views may not be shared and may not be in line with recent corporation policies, so they are only mine. Do not take it as a direct recommendation or best practices from MariaDB Corporation or interpretation that they would necessarily share. It may not be the case. So speaking about tracing and profiling, there are different ways to do tracing and profiling for MariaDB specifically, and it all depends on two things: how much code changes you are ready to do, how much you want to be involved in the code itself, and the performance impact of the tools that you use. So to name just a few possible ways to trace, I'll start with the fact that you can basically use debug binaries. In debug binaries, in the large part of the code, each start of the function and end of the function is instrumented with debug macros that allows you to trace the enter to the function and the return from the function. And there are also debug printouts and key points inside some functions as well. With debug binaries, these debug outputs can be dynamically switched on and off at runtime with specific debug commands. The problem with this approach that was widely used at the early years of MySQL development, that was quite useful, is that you have to add this code into your source code of MySQL, and debug binaries are really slow, and when they produce a lot of debug outputs, they're even more slow, so it's not practical. A thing that works for seconds may start working for days, so it's not dynamic enough. Other tracing facilities are actually embedded in MariaDB and include extended slow query log, for example. There you can trace all the queries starting from those executed for 0 seconds. And for each query, you can write down how many specific row-level operations were used, or had it tried to use temporary tables, what had it tried to sort something, and everything. That's quite useful and show query execution profile in a lot of details. But again, it's written to disk, and enabling extended slow query logs for all queries will give you a huge performance impact, while still missing some details about the internal working of the server. More tracing outputs are available in MySQL and MariaDB, including show engine in DB status, show engine in DB mutex, if it's not yet deprecated. If you speak about InnoDB internal, some of them are presented inside the information schema with InnoDB tables there. For example, you can get some details about each buffer in the buffer pool, what page is there, how many pages are used, and everything. Again, requesting this information would give a notable performance impact, and it's just one of the details. A kind of a good balancing between details and impact was found by, I don't remember, probably Google initially, who created the user stat, later used by Percona and available in MariaDB as well. So at user stat, we have a key statistics on number of operations executed by specific user, by specific client connection, on specific table, or even index. It's a very popular profiling tool that can easily help to find out, for example, indexes that are never used for days and months, it's redundant. Or the most hot tables, speaking about the I/O. One, well, actually, the first community contributed feature to MySQL back in 2005, as far as I remember, was implemented by famous Jeremy Cole, and it was profiled for queries. So the query execution was split into stages, and each stage was the time for each stage was separately recorded as a profile, and then you can show these profiles. It's still available. Show profiles allow a lot of details to be exposed about the specific query execution, why it's slow, at what stage most time is spent. Is it I/O, for example, opening table, accessing query cache, whatever. But it's also dynamic, so you can enable and disable it. It again does not provide enough details about other parts of internal server work. Performance schema that appeared in MySQL 5.5 was aimed to resolve this problem of show profiles and to provide an insight to all parts of the code that developers considered important to be shared by instrumenting them. And that instrumentation was quite efficient, so the performance counters, time, and everything was recorded into ring buffers in memory. And re-recorded when the buffer is full. So it's quite efficient, and it's still used. Moreover, recent MariaDB versions, including 10.5, added a lot of additional instrumentation, including memory and everything, and it's more or less now at the same level as MySQL 5.7. So, beside that, it's normal when you use some operating system, MariaDB there is not the only software that requires profiling and tracing, so there should be some tools created by the operating system developers to work on their own kernel code to begin with. So there should be some way to trace the kernel, and there should be some ways to profile the execution. So you can see a lot of tracing and profiling tools provided at the OS level. It can be real profilers like perf in case of Linux, or profiling tools on Windows, or it can be profiling like additional tools for profiling memory usage, for example, or for finding memory leaks, or it can be ad hoc profiling tools based on just periodic taking of stack traces like famous PTPMP. The last but not the least, you can get a lot of insights of how MySQL MariaDB works by just capturing the traffic via utilities like TCP dump, traffic on the wire. So this way you can capture the query and reply to the query, and you can see how much time is spent in between. And each network packet has a timestamp, so it's quite detailed, and it has zero impact on the server itself. So it's like a list of possible solutions. Of them all, I highlighted one that is specifically a topic for this talk. It's using OS level tracing and profiling tools. That's it. As we speak about Linux, there are 4 basic tools that I'm going to mention and speak about. First of all, the real trace interface appeared in kernel 2.6 about 11 years ago, and it's ftrace, function tracer. The ftrace appeared in a very easy way. The reason was that they had to resolve the problem in kernel, and it was an extension based on the idea of GNU profile. So when the program was built with profiling information, a special code was inserted at the beginning and at the end of the function, the same way as I explained in case of debug package of MySQL. And at these moments, data collection happened. So they extended this existing way to compile the code and added a way to dynamically replace part of the already pre-existing code with calls elsewhere. So, and then expose the resulting information via the files interface. That's ftrace. Then on top of ftrace, really soon, real profiler, as I called it, the best Linux profiler with the least impact, the most dynamic one, called perf, was added. And this was already a convenient way to add my favorite way of instrumenting the code for tracing and profiling, so-called dynamic probes. So it's possible for more than 10 years already for any binary running on Linux, including Linux kernel itself. We should use it for databases as well. On top of that, on recent kernels, starting from 4.9 specifically, was already quite complete, and specifically with Linux kernel 5 and more recent ones, even better tracing tools with less impact, more efficient ones were added in the form of eBPF, or extended packet filter. BBBBB stands for Berkeley, surely. Actually, in frames of BSD, they re-implemented tools like TCP dump and packet filters in a way that to make them applicable not only to network events. And they did it later in Linux, re-implemented it again on top of a virtual machine that safely can run in kernel context and most efficiently collect the metrics in memory buffers, like in performance schema. So on top of eBPF, raw eBPF required programming and using the related API in languages like Python, for example, or Lua. Then on top of that, command line tools, so-called BCC tools, BPF compiler collection. So as soon as API were implemented, these tools were already written and you can use existing tools, write your own. That's what a separate team in Facebook does, for example, where they use eBPF a lot. And finally, the last edition that is usable in kernels 5 point something, like on Red Hat 8 or recent Fedora and such, on recent, like few years old Linuxes, is BPF Trace. BPF Trace implemented a safe and quite interesting language in AVK style that produces the program for that in kernel virtual machines without the need to code in Python and use API directly. So you just script it, extended scripting language. So this is I am going to speak about these tools. Why not performance schema? There are two reasons. One of them is historical, and well, there are more, and I will present them. But most importantly, it's all about the performance impact. And another historical reason is being able to add probes dynamically. If you have to change the source code to instrument something, if instrument is missing, like it happened with performance schema, it's a serious deficiency for my work. I am not a developer. I am a DBA and support engineer. So I need a solution right now and here with existing code. I cannot wait for the instrument to be added. I needed to add it dynamically. That's it. So yet another reason why I do not discuss performance schema here is because it's discussed elsewhere. During this event, MariaDB Server Fest, I have another presentation explaining mostly the details of additions to performance schema in MariaDB 10.5. One may argue that performance schema is inefficient in a sense that it adds a lot of additional memory in server. That's true, and it's even more true in case of MariaDB. It changed a bit to better in 10.5, but in general, yes, you need to keep that memory buffers for every instrumentation point. It doesn't matter if it's used or not, until recently. In 10.5 and in MySQL 5.7 later, we have dynamic allocations for memory for some instruments, so it's not that bad, but it's still not dynamic enough. One another thing is performance schema may not be even enabled or compiled in. It's not enabled by default in MariaDB. It's not compiled in some forks like MySQL at Facebook. And even if it's compiled in, it still may be not enough dynamic because some instruments up to this day can be enabled only at server startup. So if you were not there and had not an idea that you need this instrument enabled, it may be too late. You cannot check memory usage of the InnoDB buffer pool unless you asked to instrument memory at startup. That's it. Sizing buffers may be a problem, so that finding that trade-off in between size of the memory additionally allocated for performance schema versus the number of details and frequency of changes that you want to capture is a real problem. So with performance schema, you may spend a lot of time trying to size each instrument properly to get the smallest performance impact and still not missing the detail. Another thing that I hit that we cannot expect, while Oracle would like us all to add performance schema instrumentation everywhere, they cannot force it, and we in MariaDB cannot force it. So, for example, inside Galera library that is quite popular among MariaDB users, the amount of instrumentation in performance schema is quite small. And we can do nothing about it because it's third-party plugin There are third-party storage engines, so we again cannot be sure how much they are instrumented. We cannot influence that. Yet another thing is usually when you are troubleshooting, solving some problems, you approach them from two sides: from your software, from MariaDB server side internally, and from the operating system side. You need to monitor operating system resources. If you use different tools to monitor and trace for your software versus operating system, you have to somehow summarize and put them all onto one plate and use together. So first of all, you pay the price twice for tracing at operating system level and for tracing at your software level, and then the results may not be compatible. So that's it. The last but not the least is the following. In MariaDB, we in support work actively and closely with developers. So when we report bugs or issues, we need to provide the information the developers asked us to provide. So they do ask us to provide stack traces whenever there is some hang or some slowdown or any performance problem. And performance schema doesn't give you stack traces. It may give you a set of stages, statements, transactions, everything, some insights following some functions in the code, but it's not a complete stack trace. So that's what we requested. We got requests for stack traces, so we need tools that produce stack traces. It's not performance schema. And for me personally, performance schema requires too complex SQL queries for many tasks, and as I do not have them, often do not have them collected and prepared, if I need to invent it on the fly, it's too complicated and takes too much time. So what do I suggest instead? I suggest to use modern Linux tracing tools. If we get to this picture of all the utilities that you can use to get performance information from, there are many, and most of them are probably known for you, from top to PS to free, SR, and whatever. I am interested in this specific part: ftrace, perf, BCC tools based on eBPF, and BPF trace specifically. As you can see from this line on the picture that I borrowed from Brendan Gregg, they cover the entire stack, from the I/O to kernel details to applications, and with libraries, APIs in between. So you can trace everything with the same tool. That's the point. This approach is quite popular for maybe the last 5-6 years, and there are many famous people who are writing about it, so just follow the links. Now, what are we going to trace, and how do we approach the profiling? There are 4 types of event sources, so we will try to capture events. So there are 4 types of event sources that we might be interested in. They can be presented in such a simple table. So first of all, there are some events in the kernel. For example, if we are tracing and dealing with I/O problems, I/O is implemented by the kernel, so at some level. So we may be interested in what's happening at the kernel level. And there are event sources in applications or in user space, as I put it here. Now, from another dimension, it depends on pre-existing instrumentation that was in the source code of the kernel. Then it will be a kernel trace point, or in the source code of the application software. It's like what happens with performance schema probes, just they are not accessed by these tools. These are so-called user-defined statical tracing, userland statically defined tracing as well, simply dtrace probes. Based on dtrace in Solaris, that was the first dynamic tracing tools widely used and like a father of all dynamic tracing. We do not use Solaris anymore these days, and dtrace, while it's present in Oracle Linux, theoretically is not easily available outside. So kernel developers of Linux had to invent other options. So manual annotations mean that you have to change the source code, then recompile, and then you add event source. It's inconvenient and it's not dynamic. So another way is to add dynamic or automatic probes, and this is what we are interested in. So you can do it in kernel context, and it will be a kernel probe. Basically, you can add probe to any kernel source or function, or you can do it at user level. That's my point of interest for this talk, so-called user probe. So you can add tracing events dynamically to functions without changing the source code. That's the greatest way to do things. So, okay, you have event sources. Let's assume you somehow defined some events for your software, for MariaDB. How you can access the event sources based on the tracing framework that covers the entire system that I am going to discuss here. It's Linux, so it's Unix. Everything should be available through some files. So yes, you get access to event sources via the files in a special kind of file system, TraceFS, that can be mounted on sys or elsewhere. Here, let me finally go to the terminal, and here is what I'm speaking about. So we have TraceFS mounted here at syskernel tracing. So then we can just check syskernel tracing, what is there. Now the first problem that I'm going to mention with this tracing approach is that you need sudo or root access. So unfortunately for developers who do not own the server they work with, it may be a bit complicated. But yes, that's what we have there, a lot of subdirectories, files, whatever. And they will be dynamically added and removed depending on what tracing facilities you do. So how do you deal with files on Linux? You read files and you write to files. So that's the basic way to deal with event sources. You can do it from command line, you can do it from the system calls, that's it. As a result of your writes to some files in this TraceFS file system, the source code of the functions is modified on the fly to add tracing events. When you are done with it, you stop tracing, that instrumentation is dynamically removed. So you pay the performance price only while you are tracing. So you can add trace points dynamically and remove it when they are not needed. You can add them on the fly only for the period that you need, and you do not use neither CPU nor memory when you are not tracing stuff active. So these files, numerous files, are not so easy to deal with, easy theoretically, but a lot of commands to type in practice or a lot of code to write. So we need some front ends. With time, when this dynamic tracing system evolved, on Linux kernel, several front ends were added. The first was perf, then BCC tools were added, then the latest one is BPF trace. They're all front ends. Front ends are truly optional. So as soon as we have the file system mounted, that's how it's mounted if you don't have it. We see some files there, we have seen that. We can check what is there as we were interested in dynamic user level probe. So let's check uprobe events. Tracing uprobe. Yes, so what is it? We can get access. It's a simple file. It's empty now, so there are no user probes. The file exists, but it's empty. Okay, so to add the probe, we had to write something there. Then it will not be empty. If you do not want to write something there manually, you can use tools based on top of these files, command line driven, that already simplifies this process for you. let's skip it. And we can still do it manually. Let's assume that I would like to add a trace point, a probe, to the dispatch command function in the MariaDB 10.5. So the first problem that appears if I use ftrace directly is that I need to find out the address of that function relative to the binary. So because for the probe, I have to provide the address. Ftrace does not know anything about the source code. It just needs to know the address and try to do something with it. So how to find the address? To find the address, you can use the obj dump. There are different ways. It's just one of them. With T option, provide the binary and then search for the command. Here is the address. You can see the function name is mangled because, well, that's the way it works. We may have to use mangled names later with other front ends. So with ftrace, we need just address. So we can add a probe P. We can give it optional name. If we do not give a name, then the name will be inferred from the binary name and function name, or whatever. So we give explicit name DC. The binary is listed here. The address is listed here. Then for dispatch command, we would like to print the query, which is the argument. The argument number 3 for dispatch command. Here, it would be interesting probably to find out how do we know. We need to know the source code. We can study it, or we can use it and study with GDB. So we can attach GDB of MariaDB. I already used branded names for 10.5. It's MariaDB. So if we attach to the binary, we can add a breakpoint, for example, dispatch command. So then if we try to, for example, connect to MariaDB, surely we have to continue here. Okay, so that's it. We started and we already executed some command. So our breakpoint fired, and here we have a query. We can see it as a third argument called packet. So here we can just print the third argument and see the query. It's asking for the version. So if we queue it from here, that's the knowledge we need to add dynamic event as well, user probe. So we detach from GDB, get back here. So that's what we do. We need it's a third argument. We should know how arguments are passed for our platforms for ftrace. Its third argument is passed by the register in the register that should be accessed as DX. So not extended, just DX, trust me. And I'm printing the content of the register. +0 is also important to get the address right, 0 terminated, as a string, and we give it a name of query. So if we write this text to the uprobe events, we can append it. Now we just overwrite, but if there are many probes, we have to append. And then enable the specific probe, and then enable tracing. We can then read the content of the file, some file. There are several, depending on what you trace and how you trace. For example, trace pipe and get the resulting query. So the idea of this test was to capture the queries on the fly. You can do it for 11 years already. There are details presented in my separate blog post. So you can access event sources and add dynamic probes with nothing but ftrace. You do not need perf installed. You do not even need GDB. All you need is objdump to find the address and knowledge of the source code. That's cool enough. So what are the problems? The first problem is already known. You need root access. How to get address? Well, objdump helps. It may get complicated, unfortunately, with C++ and other modern software, with Java, for example. I am trying to show some of the problems and solutions in a separate blog post. How to work with function arguments? Okay, if it's just a simple argument that can be used as is, as in our case, we just need to know how it's passed. But what if it's a structure? So eventually we can access any memory area. It's not going to be safe, but we can try. And well, probably we can figure out how to print structure as detailed as thread, for example, in case of MySQL or MariaDB. But it's complicated. So this tool works easily only for simple functions, ideally written in C. Then what if we would like to add a trace point at the end of the function? For example, let's consider allocating memory. If we want to trace memory allocation, we probably need to know the size of the allocation and the address that malloc function gave you back. So with this address, you can then store it somewhere and then trace also the free, and then you can see if something remains after some time of working, how much memory is allocated in total and everything. So for the probe at return from the function, there is just another type of the probe. It's R, return probe, and you can access readval. The return value from the function. Again, you can print it differently. You should know the data type. There are only a few basic data types supported, so it's all getting complicated. When you are done with the probe, you can just clean up everything from your probe events, or you can just remove the probe by name with minus. In more or less complicated cases, I had to, and that's my suggestion, actually use a front end like perf to add a dynamic probe and then check with the tracefs mounted how the probe looks like. That this way you can study how it's done. It's complicated, and I'm going to spend more time with months and years on how to do it with pure ftrace, because ftrace is always there. Some customers may not be able to install additional packages due to their internal security reasons, but they do have ftrace. So they may still have problems with root access, but that's another story. Then with no root, all this is not for them. So the oldest front end is perf, which is actually a sample-based profiler. But we will use it for adding dynamic probes as well. Perf basically, it has dozens of commands, allows to record the profile, to create a report based on recorded profile, to show the recorded profile data. Perf top is kind of top, but with top functions. It's interactive utility showing what spends most of the time based on your sampling. And actually the way to add a dynamic probe with perf is perf probe. What a surprise. So with perf probe, you can add similar probe to the one we already discussed previously with a much more user-friendly command, just dispatch command. Is a function we want to trace, and we want to print packet. We already seen it's a variable. It's variable name as a string. No mangled names, no addresses. That's it. Then we can start recording. It's sampling profiler. We can set up the frequency of recording so we do not miss any calls, or without frequency it will be picked up automatically. So we can do recording for some time, for example, until we stop it. And then we process the result with perf script, and then with this probe added, we can see the query is captured. That would be the output from MariaDB. When we are done with the probe, we can delete it by the name. So that's easy. The name of the probe will be shown to you when you create the probe. So you will see that the name is like probe dash binary name, short MariaDB D, and then a colon and actually a function name. The rest are optional parameters. So yes, we can see the queries. This way, moreover, we can also see the binary, process ID, CPU or core on which it runs. There is a time starting from the start of recording, so we can see how much time was spent on our probe. Then the probe name and probe arguments. There is also the address. So you can do a lot of things to control this output format. As it's visible from that simple example, it's way more user-friendly than iftrace, because you can use names, you can access, in many cases, you can access complex structures, records inside records with pointers and everything, not always, but often. And still, while it's more easy, you may have to study source code and do some checks in GDB to find out what exactly you would like to print. Problems. Are there any problems? Usually no, but for example, when I tried to use this approach for MariaDB 10.3.18, as far as I remember, on my old Fedora box provided by Fedora, it was Fedora package, at that time, that same function dispatch command was implemented differently. It had a com-data structure argument where the query was in com-query point query. And when I tried to add the probe, it had not worked. I was not able to dereference this the argument properly. I had not spent enough time and I on that and decided to go an easier way. There is another command in the stack for looking for the queries. It's do command, and at that version it had also the packet, and packet contained the SQL statement. So I tried to add it and I failed. So whenever you cannot add the probe for whatever reason, you see it. So the packet was a local variable at that moment, and I was not able to access it at this stage. I could access thread parameter, but it was too complicated, and I was not able to figure out how to do it. So what I did, first of all, I was able to check that theoretically in perf you can access all the variables. So yes, I was able to access the thread variable. That was the only argument for do command at that time, but I was not able to go farther. Next thing, that packet was a local variable that was available, and later, this is how it was declared, and it was initialized later. So there was a way, and there is a way, to add a dynamic probe. As you can remember from ftrace, it's added to the address. That address is not necessarily the beginning of the function. Actually, any executable command can be replaced by the interruption code int3, and then the probe can be added dynamically on the fly. So to find out which lines of the code can be instrumented, there is a line, not lines, or it's a typo line command. So for the specific function, you can show a line that you can attach to. And of all the lines, I found out that line 157 is the one where the local variable packet is already declared. And it should get the proper value. So I tried to add the probe there. The syntax is quite simple. You add the probe to a specific line of the function. You can add the probe actually to a specific line in the source code file with another syntax, but similar. And I print a variable named packet as a string. And I've written down everything, started recording, and got my queries again. So what's the lesson we get from this? All this exercise was a result of the fact that simple command had not worked. But I found out that with perf, you can easily, it's a convenient front end, you can easily add a probe, dynamic user probe, to almost every other line in the code, and access local variables there. So it's the most dynamic way to trace things you can imagine. You can add the probe after every other line in the code, before it and after it, give names, and measure the time spent executing this specific line of the code. Not without, not with recompiling, not with adding performance schema instrumentation, not without waiting for anything, just on the fly, and it works. Besides user probe, you can surely use kernel trace point. For example, it's needed when you try to measure time spent on I/O, for example. You can do tracing not only for MariaDB server binary itself, but you can trace shared libraries as well, those that are dynamically loaded. This is how I trace malloc calls and size of allocations. This same approach was already applied by my colleagues in MariaDB to a software called MaxScale. You probably know about it. So it's not even a server. You can apply it to anything where a memory leak was suspected. So all the details are already shared in a blog post. In another blog post, I've tried to apply it to C++ and was successful. That was a case of MariaDB 10.3. In 10.5, I found out that this member function became virtual, and for virtual functions, you are not even able to add a breakpoint in GDB. So you cannot trace it, or at least there is no easy way to do it. So these practical examples show you that problems are real. Not all of them can be avoided. Just a few words about perf as a real profiler. That's the first use for it for myself. Perf is easy to install. Perf is easy to use. For profiler, you usually, as it's sampling profiler, you usually set up a frequency. How often, how many times per second you want to stop the execution and check your trace points or capture the stacks. That's how profiler works, and measure everything. There are default frequency. It can be self-tuned by the perf itself. 99 samples per second is usually enough. Then you can record forever. The more you record, the more data are recorded. The data are sampled by reading from that tracing file system, and they are put into the user space. Writing files into the user space takes time and resources and disk I/O. So usually you do not profile for days, you profile for a short time. So you can profile just function calls, or you can also write down stacks. So with -G, you write down also stacks. You can profile specific CPU or all of them and many more things. So you record your profile. When you are done, you can, for example, stop recording the one way or the other. And you can get the profile. You can get it dynamically too. I will just show that for the, let me queue it from here. For some samples, I have a sysbench command running, and in another terminal at the same time, I can do like perf top. Yes, and you can see where most of the time is spent at the whole system level. It might take some time. The load is really high. The frequency is already decreased. So let it work for some time. As a result, if you are writing down stack traces, you will be able to get a tree of function calls with percentage for each. Oh, here it is. So we can see that, for example, most of the time is spent on Unix. A lot of time is spent in MariaDB. You can step inside, zoom into the thread. See, it's dynamically changing. So when you are done, you can queue it from it. Sorry. So I will not overload the machine while it's recording. So one of the basic examples from my blog post, probably 4 years old already, shows a case that turned me to dynamic tracing entirely. So the case was simple. At customer side in a complex Galera setup, simple queries like select single line by primary key often hang for 13 seconds, for example. And the idea was to find out why they are slow sometimes, sometimes not. There was a lot of concurrent activity and everything. I tried everything I could with performance schema, show profile, and whatever. And I found out that a lot of time is spent at statistics stage. So calculating statistics. What statistics? Why? It was not clear why it takes so much time until I've got a profile with stack traces. Here's where the most of the time was spent. So yes, it was in statistics. We were reading the data from the table. You know, in InnoDB, when you need to find the plan for the query, and you are looking for the key, you have to find out how many rows you may get for this key. So it was really a reading of data from the table. And why it's slow, why reading one line is slow, it was waiting for in the QE to enter the InnoDB. The problem was really that in that case InnoDB concurrency was limited. So when there were other, for example, 12 queries for 12 cores or doing something for quite a long time, like doing big updates to unrelated tables, such a simple statistics request was blocked. So the resolution was simple, remove the limit, but I studied quite a lot on that. Among things that I studied was that performance schema is not detailed enough. Performance schema does not document stages of statistics calculations and many more things. But really, dynamic tracing and using perf profiler was a solution to a real practical problem after everything else had not worked. And the detail was missed surely by me, and everything depends on the load. Under some load, everything works, then it does not work. So we tried to capture the statistics for and the information for quite a lot of time. In practical cases, the call stacks and such graphs, they may become huge and not easy to work with. The samples collected themselves can be huge. So when I was collected I/O requests at kernel trace point for 60 seconds, it took 33 megabytes. Writing 33 megabytes on some hardware may be already time consuming. So, to summarize, what are the main problems and challenges if you have root access and you mastered the tool? There are two. First of all, perf at the front end that writes everything to the user space is having too large impact. What is the solution to these problems? Use a lightweight tools. So if it would be possible to process the data, not after the fact, after the collection, but on the fly, that would help a lot. If that would be possible in the kernel context, without touching the user and passing to the user only the result that is needed, that would be perfect. And ePBF gives us that. And another question, what to do with such a complex profiling information when it does not fit on many pages on screen? So you have to summarize it somehow. The answer to this is post-processing tools. Of them, the most popular right now are flame graphs and other heat maps. So you have to summarize and visualize this data in a way that are easy to use. That's a bit beyond the topics of this talk, but you will see how it looks like. So, as a way to reduce the impact and trace safely and summarize safely whatever you need, eventually eBPF was developed. When porting dtrace proved a hard task and stalled. eBPF is based on backlink packet filter that is behind TCP dump. The idea was that filtering should be executed at kernel context, so efficient, but it should be safe, so it should be in some virtual machine. So they had rewritten the code to run in a virtual machines that was efficient because the code for it was JIT compiled, just in time compiled to the machine code. So there was an extra level of safety, there is an extra level of verification before the code is allowed to run in eBPF virtual machine, and for this eBPF to be useful not only in network stack tracing, it was provided access to kernel probes, user probes, static trace point in application sources, performance events, and almost everything. Same as performance schema, eBPF writes down to the memory areas in kernel. And then these memory areas can be read by end user. So it's as efficient as performance schema. Maps are limited in size, so memory is also not abused. And you have access to all the internals in the kernel. And you can summarize things in the kernel. So more or less up to the kernel 4.9, all this machinery was implemented, tested, and widely used. So the problem was with front ends, how you write the code. You can write LLVM, it's LLVM virtual machine actually. You can write assembler code for LLVM, but it's too complicated. So there were APIs ported to Lua and Python, and at this moment people started to create a lot of tools in Python doing all kinds of things. For example, access to dtrace, static trace point that some software still had supported. So it's like people decided to stay dtrace compatible when they implemented different previous tracing frameworks for Linux. So we can, for example, do that same thing as we did printing queries on the fly using a static trace point if it's defined. So that's how it works. I should say that MariaDB binaries do not provide dtrace, and MySQL 8.0 just removed dtrace probes entirely. Fedora conveniently had them compiled, so I was able to capture the queries this way without anything else, just by using a ready-to-use BCC tools and already existing in the code static trace points. So the same way with trace, you can add with similar tool called trace, you can add dynamic trace points. You will still have to use mangled names. You need to know how arguments are passed. You can see it in my blog post how it works. So you can write your own BCC tools code in Python if you're a developer, and entire teams, as I said, in Facebook, for example, that's their main job, to write such a code. If you're a DBA or a support engineer like me, not a developer for decades, if you do not have Python installed, you may still write down quite efficient custom tools to summarize the information provided by the kernel using the newest front end called BPF trace. So it does not work, for example, on the machine I am currently working on Ubuntu 16, but it's really old. Whenever you have kernel 5, you already should have a working BPF trace. There were some problems on Fedora 29. Starting from Fedora 31, they are mostly resolved. That's based on my experience and what I was told. How BPF trace works? You can actually study the tutorials, but basically you provide a program. It's like AWK. So the program looks like you have a pattern. If something matches the pattern, there is an action. So it's a set of pairs pattern action. So if you see something, you do this. As an action, you do not have loops, unlike in AVK. So there is a guarantee that BPF trace program always complete. It cannot hang, cannot loop, cannot hang the kernel virtual machine. So you add the trace. You basically add the trace point. For example, syscall, sysenter for all of these. For a specific syscall, like here. So it's a pattern. So whenever we see this call, we do print the arguments. So these are open files, for example. So basically, that's it. You define several probes. Then you can match additionally the probe against some filter, and then there is action in curly braces. So how it may look like in practice? Besides trace point, BPF trace is also able to act as a profiler. There is a special probe called profile. You can set up frequency, same as with perf. You can add a filter. For example, you do not profile the entire system as we did with perf top. You profile only MySQL D, for example, or MariaDB D. And then what you can do, you can print user stack, in a perf compatible format. There are two kinds of formats, and you collect stacks same as we do with per profile. Here is the content. So we do calls, dispatch command, do commands, everything. Thread pool was active, so we have a callback here. So you can check my blog post for details how to use this in practice to have a both user space trace and kernel space trace sampled 99 times per second. This is how it works. Why should we care? Why should we bother? Because of the performance impact. So with eBPF, no matter how you access that, maybe by BPF trace, you have the smallest performance impact. I was running similar sysbench test on another system, and I've checked the queries per second executed with different dynamic tracing options. PTPMP, poor man's profiler. So we got a drop to just 56% when we collected once per second and missed many samples. If we try to collect more often, just all hands. With perf record, we had 98% of queries per second, so there is some performance impact, mostly related to writing down this amount of data. And with BPF trace dynamic profiling probe, when I've counted, similar to what we did above, I've counted the number of unique stack traces. So I've got just 0.13% of negative performance impact with 99 samples per second. With higher frequency, it will be much worse. Few words in conclusion on how to represent the data. You can read a lot about the flame graphs. All these tools, dynamic tracing tools, their output formats are taken into account in this set of tools developed by Brendan Gregg, so you can process stack traces from PTPMP, from perf, or you can pre-process whatever stack traces you see. You can use BPF trace directly. You can use pre-existing, pre-built Python-based BCC tools. For example, if we try to find out where the time is spent, if it's not on CPU, we can use the existing off-CPU time utility, produce text, then collapse them and present them graphically. We see where most of the time is spent here. Let me summarize the problem of dynamic traces as we are going out of time. So, first of all, you need root or pseudo access. In some cases, you need literally root access. As I see from my experience, and as we could see maybe from samples I will share during the chat with you, there is a problem to debug the problem, the program when it is traced. So GDB sees a different code than it expects. It does not really work. So it's still a problem to find out the amount of additional probes and the trade-off in between the details you collect and the amount of memory and CPU you spend on collecting. Adding dynamic probes to C++ and complex code of that kind or to Java may be problematic. Using BPF trace to access source code may be more problematic than perf because you have to pass headers. It needs to know structure. Surely for all of this to work, you have to build with a no omit frame pointer. If we cannot get the frames, we cannot get the information. In case of pre-built packages, we may need debugging for packages so that symbolic information is available. In some cases, we have more tools to install, but with ftrace, it's always there. The most important with all tools above and beyond perf is a lack of current practical experience. It's my own problem as well. I had not used them often enough to really be fluent with them. But I am still not the only one who is suggesting this stuff. People do dynamic tracing even for Oracle or DBMS, and you can find out a lot of other additional sources of information about this. So that's all from me. As usual, if you ever see a bug or a problem in MariaDB, report it. Thank you very much.
Valery Kravchuk, thank you. First one could see a trace of you, and now we can see, both hear you and see your face. That's great. Progress.
Yes, thank you very much. MariaDB is getting better with every release, and my presentations and presence is improving with every attempt.
So it seems. It's late night for you. At least it's late night for us here in Finland. What time do you have?
Almost midnight, same time as yours, I think.
Almost midnight in the Ukraine as well. Okay, so let's go to business or to technology. So traces, you showed 4 different ones. Which one is your favorite? Which one is the best for DBAs? Perhaps those are 2 different questions.
Well, the best for DBAs at the moment, probably, and the easiest to use now is surely perf. The best for DBA, it's because it's usable on all the Linux versions they should have in production. And it's easy to use, and it covers all the details. It does not require you to deal with mangled names. It allows to access structure members and everything. So that's what everyone should know and try to use. And that's what I use most often. As for the long term, and for those who are interested in the lightweight tracing and monitoring, long term you should move to eBPF. And as for DBAs, it would be BPF trace, as it allows to easily create small useful utilities. Now, as for me personally, I am mostly interested at the moment in ftrace, the simplest file, oldest interface, and the reason is simple. That's what every customer does have. No matter what they installed in their system, it's there and ready to use. They may not be able to build anything from source, they may not have any new Python, do not want to develop or allow to install any additional package, and still with ftrace, I can get most of the things if needed. So personally, I would like to improve in ftrace in upcoming future.
Okay, and there still are 4 of them. So and you did present the others. So when does it make sense to look at the others?
Yes, it makes sense to use BCC tools if you are going to do lightweight tracing in production for the full stack. So that's the most universal and least impacting solution, but it requires a development. So you need to know Python, kernel details, source code of your system, and everything. That's the most flexible thing. You can do anything with that. So all 4 of them have their own use, and big companies like Netflix or Facebook do rely on BCC tools and Python or Lua programs they create for each and every specific issue, for each new system, for each new software, for each new performance problem. And they keep them running for days again in production. So that's a big deal. For simpler people like me from the field who just step in support to resolve one-time problem, I cannot afford spending time developing software that may never be installed and that I will not get installed on the next customer site or for the next issue. So I rely on simpler tools. But those who manage bigger server farms, including container-based environments, the future is in eBPF, BCC tools as the most powerful, and BPF trace as a fast and dirty way to check things right now, right there. Both of them require kernels 5, the newer the better. So that's also important. If you are going to upgrade to recent Linuxes, new tools, BPF trace and eBPF in general is a thing for you. If you have to use still old CentOS, old Ubuntu's, old Debians, or need a solution that works everywhere, you have to rely on perf or even if trace, like that.
So, interesting to hear you describe yourself as simple persons in this context. That's very, very humble and noble of you, but I would want to hear some war stories of using this type of dynamic tracing when you work with support customers. Do you have any juicy stories?
one of the quite recent stories happened to a big customer here who needed like tens or many tens of thousands of concurrent connections for whatever reason. So surely they used thread pool in MariaDB, otherwise it would be hard to get the result. And at some stages of their production or pre-production use, thread pool stuck in some weird cases. So that's exactly when perf, profile, and stack traces got at this very moment when it hangs, were really useful, and it helped to find out the problem, resolve it, and add features to MariaDB 10.5 to make it easier next time, both to find out what happened and to prevent such a problem. So as soon as our developers in MariaDB Corporation get stack traces during some problematic load, the solution is inevitable and it will eventually be developed. The problem is to capture things. That's why dynamic tracing. And that is how it was really useful. There are smaller cases in development as well, but this was a real life, big, one of the most important support customers who was able to proceed or at least understand what happens just because somebody was able to apply perf, explain them how to install it, how to use it, and they did it themselves because we in support here do not work at customer systems. We tell them what to do. That also proves that dynamic tracing tools are for normal DBAs as well. You do not need to be a developer. Simple instructions, simple commands to run at your site and share only the essential data. We do not need your private data. We do not need even huge core dumps for some cases. We need just a trace taken at the proper moment with the right level of details. And that was what dynamic tracing in Linux gives us.
Sounds great. So I have one short concluding question. You have about half a minute to reply to it. So the escalation part of this, I suppose, this is not for your average support cases, but how do you scope whether dynamic tracing is really needed to solve a support case?
Well, as soon as something hangs, there are two options actually. Either apply GDB and get back traces, or if it does not hang, or if you cannot afford, does not literally hang, something still works, you cannot afford to stop processing for other threads, then dynamic traces is the right thing to apply. So complex performance problems in production, I would put it that way.
Great, simple answer to a very complex situation. Thanks for the hour-long presentation of dynamic tracing. Really cool stuff. Thank you, Valery Kravchuk.
Thank you.
Now for Scaleflux and Seth Shellnut, MyTile, a cloud-native storage engine based on TileDB.
Hello and welcome to the session on MyTile, a cloud-native storage engine based on TileDB. My name is Seth Shellnut. I'm the Chief Technology Officer at TileDB. Before we get started today, I'd like to say a big thank you to the MariaDB Foundation for putting on ServerFest 2020. I know the pandemic has changed the plans of the usual MariaDB conferences, and we're very appreciative of them getting this put together. Today we're going to talk about what is TileDB, an overview of MyTile, the use cases of MyTile. We have two use cases we'd like to highlight in particular, and the internal usage of MyTile at TileDB today and how we use that in production. So what is TileDB? TileDB is the universal data engine. It's built upon a multi-dimensional array format, and this enables storing and accessing dense arrays. This could be images or video, sparse arrays, which can be things like LiDAR or genomics data or others, data frames, which is really any data in tabular form, most commonly SQL tables, and these are most commonly stored as sparse arrays. And also key value data sets, which are typically stored as sparse arrays also. So when we say universal data engine, we're really talking about a whole number of tools and integrations and details about TileDB itself and the format and the core library. So the TileDB core library is this multidimensional array store, and you can store any highly structured data in the TileDB format, and you can efficiently slice and do and perform computations on that data directly in the cloud. We have a number of efficient integrations with TileDB and APIs that are in Python, R, Java, C, C++, and more. We also have a number of efficient integrations with things like Dask and Spark and PrestoDB, and of course MariaDB, which we're going to talk about today. And this efficient integrations and APIs allows users to analyze their data with any tools that they prefer. If you are trying to use some Python machine learning packages, TensorFlow or Keras or something, you can use that directly with our Python API, or maybe you want to issue a SQL query via MariaDB or use PySpark. The options are completely at the user's disposal as we provide efficient integrations for the whole package. We also have a SaaS offering, TileDB Cloud, which expands upon the universal data engine and enables planet-scale sharing of TileDB arrays and datasets beyond just your organization, but to the public at large. And we also have a number of hosted components to TileDB Cloud to eliminate some of your deployment hassles. Hosted Jupyter notebooks for easy exploration, scale-out computations via serverless user-defined functions in languages like Python and R and others, and serverless SQL, which is built upon the MyTile storage engine, which we'll talk a little bit about later in this presentation. So some of the core features of TileDB and the format itself are it's cloud native, so you can store your data in S3, in Google Cloud, Azure Blob Store, along with things like HDFS, POSIX file systems, and more. We have a unique tiling and chunking format that provides fast slicing on your data and atomic I/O operations. It's a columnar format, so all of the fields and attributes are stored as independent files. We have a multitude of compression, encryption, and checksum filters, things like ZSTD, LZ4, and more. The entire library is built around fully multi-threaded implementation using modern C++ standards. We support massively parallel I/O operations, which works fantastically well with the cloud object stores. We have data versioning built directly into the format itself. This provides rapid updates and time-traveling capabilities. TileDB also supports arbitrary metadata on arrays. These are key value stores where you can put any type of metadata about an array on there. You can also have groups of TileDB arrays, and this entire thing is packaged up into a very nice embeddable C++ library. So some of the features about TileDB itself that I want to kind of dig into before we talk about MyTile are things around time traveling and the MVCC design that allows that. So to start with, every write in TileDB is immutable. Every write goes to a new, what we call fragments, and new objects are created. And updates are treated just as writes. They're completely immutable, and new files and fragments are created. And this is very important for cloud object stores where objects are immutable and you're not allowed to update single bytes. This also provides a number of benefits, time traveling being one of them. So if we look at the diagram that we have here, we have three writes that occurred. At T1, we wrote the 4x4 array. At T2, we wrote a subset. And at T3, we wrote a very sparse subset all over the place. After T3 occurs, the logical view of the array has all of the updates dispersed within it as you would expect. The power of TileDB and the MVCC design, though, is you're able to time travel and go back to any of the previous timestamps, T2 or T1, and open the array and access the data at that point and see the array as it was at that point. So if you open it up at, say, for instance, T1, you get to view and access the original data of the array before any updates were applied. Now, this object immutability is also very important with the crash safety of TileDB. So we'll talk a little bit more about the assetness in a moment, but you're crash safe based off this immutability. If a write fails, that fragment and that timestamp is simply ignored in subsequent reads. Now, a little bit of a technical note I want to hit before we move on is we do have something called consolidation supported. And as you expand this out, you can see that if you keep these timestamps over time and these fragments over time, there could be quite a lot of them. So we do provide the ability to combine and consolidate the fragments into a super fragment and purge out the history if you desire. This can reduce the disk space and can also potentially improve the performance. It's a complete optional feature. It's up to you, the user, whether you want to perform this consolidation and purge out some of your history or not. And then we or not. So TileDB supports the immutable objects, and that leads directly to our asset support. So all writes in TileDB are atomic. I mentioned previously we have a tiling structure and a chunking structure. That gives us the atomic I/O units that we are able to write. Consistency is determined by the storage location. So TileDB, supports object stores, which are eventually consistent. We also support, POSIX file systems, which do support atomic operations there. With the eventual consistency of object stores, that's natively handled by TileDB. TileDB will always return valid results, and we will never return corrupt or invalid results for a query that's given. So the eventual consistency is built into the format. No external service is needed, or external libraries or plugins or anything is needed to handle that. It's built into the format and that MVCC design. Isolation and durability is inherent in the MVCC design. Since every write gets its own fragment, which is basically a folder or a prefix, there's no collisions. Every fragment is unique with a timestamp and a UUID, so there's no collisions that occur between two writes. Transactions and locking are simply not needed for TileDB, and you get the full multi-reader, multi-writer design without this. Conflicting writes that happen at the exact same timestamp, while how unlikely do occur, those are handled natively by the UUID, and the ordering of that is based off the UUID. So let's talk about MyTile for a minute and go into the details about the MyTile, the storage engine based on the TileDB embedded library. Now, one of the big benefits of MyTile is that it inherits all the functionality of TileDB itself. So it uses the embedded C++ library, and now you can natively access through MariaDB TileDB arrays that are stored on remote cloud object stores like S3 or Google Cloud. We support full dynamic discovery in MariaDB, so you can simply run a query such as select star from an S3 path where a TileDB array exists, and it just works. It just works. You are able to query the cloud object store natively directly without creating tables or moving anything or doing anything but issuing a select statement. And we have complete interoperability with all the existing TileDB arrays and other APIs that we offer. The MyTile is based on TileDB itself. There's no semantics. There's no difference in the actual storage format itself. It is the actual TileDB arrays that are accessed and used directly in MyTile. Now, I do want to make a note ahead of time here that the MyTile storage engine is currently maintained by TileDB Inc. It's outside the MariaDB source. We are hoping to upstream that soon. Now that MariaDB 10.5 is out, big congratulations to everyone getting 10.5 GA'd. We're hoping to work to upstream that soon. So there's a number of features and optimizations that we've done with MyTile to work closely with TileDB to offer a lot of performance and benefit for the large workloads that we're targeting. We're targeting a lot of the large OLAP style workloads where you want bulk access, bulk writes, bulk reads to do large aggregations and things like that. So one of the first things that we did was support condition pushdown. So we do support the indexing and primary keys that you would expect based off the TileDB dimensions. However, we also built in support to MyTile for condition pushdown. And this provides an increase in performance for a large number of queries. The MariaDB Query Optimizer does a fantastic job, and it's a great piece of software. However, there's certain cases where the optimizer might choose not to use a certain index or might go a different route. And because we know that TileDB can handle certain predicates on dimension fields very efficiently, we intercept those predicates where possible and push that down and those operations down to TileDB to do more performant accessing of the data. Besides condition pushdown, we also optimize with multi-range reads, and this allows for high-performance joins between TileDB arrays through MyTile and other tables in MariaDB. They could be InnoDB tables, they could be other TileDB arrays, but basically the MRR support gives us this bulk key access which allows us to very efficiently and very performantly query the TileDB data to fetch the relevant parts that are needed in bulk to do that join. Let's also take a moment to talk about transactions and the locking support in MyTile. So as I mentioned, TileDB is a lock-free system for multi-reader, multi-writer. The TileDB storage engine and format itself natively handles the conflicts with the fragments, and so there's no need for any locking inside MariaDB. So MyTile itself does not implement any locking, and you get a completely multi-reader, multi-writer experience as you would outside of MariaDB. And without this locking, we still support all the ACID-like functionality that TileDB natively supports. And so you do get the eventual consistency of cloud object stores as kind of the main limitation and full ACID compliance there. But without any locking or transactions, you do get the same guarantees that exist outside of MariaDB with TileDB itself. Now, transactions are supported only for bulk insertion of data. So if you are inserting multiple records in a single transaction, that is supported, and those records will be collected and then committed at the final commit for a bulk insertion. However, no general transactions are supported, and the rollbacks and advanced things like checkpoints and whatnot are not supported at this time. TileDB itself does not have transactions. It does not need transactions for the ACID-like support that we have. However, it is on our roadmap to consider MariaDB single server transactions and add some level of support for that. And then also, we are looking in the roadmap to add some sort of orchestration layer or something for TileDB itself to support a level of transactions, as there are some edge cases where users might want those. Although, like I say, for most of the use cases, the multi-reader, multi-writer MVCC design of TileDB gives you everything you need and would expect from the general transactions. So one of the super cool things and things that I'm really excited about with MyTile is the usage of MyTile with the embedded MariaDB instance. So MyTile can be built and bundled into a single library with the embedded MariaDB instance. And we have customers that have used this, and we promote the use of this to facilitate exploring the data and do lightweight manipulation of your data. It works really great in combination with like a Jupyter Notebook to be able to access a TileDB array that's stored on a cloud object store without having to spin up a MariaDB server. So right from your laptop or right from a remote server in a single Python environment or other environment, you can query an array with SQL without having to spin up a remote server. And the MariaDB embedded library is fantastic, and I know it doesn't get a lot of love in the community and not a lot of people use it, but it's really a fantastic little piece of software and mode that it can be compiled in, because the MariaDB library effectively has the same API as the MariaDB C connector. So you can drop the embedded library into a number of clients, such as one of the Python clients, you can do the Java client, the R client, anything that links against the MariaDB C connector, you can drop the embedded MariaDB into, and then get SQL queries working on TileDB arrays without needing to set up a server. Now, of course, there are some limitations of the embedded MariaDB instance. You're having to fetch the data to your local machine where it's running, and you're constrained by the resources of that machine. So if you're working on your laptop, you might be pulling data across the internet, and you have limited RAM and CPU resource. But we do think that it provides a lot of benefit for initial data exploration and lightweight usage. I want to take a moment to discuss backups with MyTile. So TileDB arrays are self-contained in the folder where they exist, or the prefix on an object store, and you can simply copy that folder. The array is always in a consistent state, even in the middle of a write. The MVCC design, we use special OK files to signal when a write has completed and when they show up with the eventual consistency. So at any point, even in the middle of a write, it's safe to copy the entire folder out or copy parts of the folder, and you won't risk any corruption of that backup. Only potentially an incomplete write that might exist. So this opens the door completely to the hot backups and incremental backups in a very, very simple manner. The structure of a TileDB array is very straightforward, well documented in the spec, but it's very straightforward even if you just list it yourself. And this opens up the possibility for you to make an initial copy of an array and then incrementally only copy out to backup the new fragments and the new parts that are written. TileDB arrays work fantastically well with tools like rsync or the AWS S3 sync commands or the equivalent Google and Azure commands. So it's very easy to copy the data sets around and have consistent backups. So we've talked a lot about what MyTile is, some of the features and some of the optimizations that exist. Let's talk for a minute about what it's not. So MyTile is not a general replacement for InnoDB. It's not geared toward the general transactional data sets and the highly transactional data sets that InnoDB supports well. InnoDB is a fantastic general storage engine that's been around for quite a while and has great support. And MyTile is more geared toward the OLAP and the large data sets, the terabyte size data sets, than it is for the highly transactional data sets that InnoDB does. Also, MyTile is not designed for full text search and indexing capabilities today, such as for storage engines such as Runga and others that are more specialized. TileDB gears more toward the general OLAP use case that exists. So let's briefly do a quick comparison between InnoDB and MyTile, and then we'll also look at MyRocks and MyTile. And to start with, I want to say this comparison obviously is at a high level. It's not complete. We're happy to discuss in more detail some of the comparisons after this session. Some of the advantages that MyTile has compared to InnoDB, of course, is first off, it's cloud native, so you can store your data on S3, Azure, or Google Cloud, full read-write support, and you're not limited to the data directory of MariaDB. Of course, you can write your array to the data directory. You can write it to a local file system or anything that we do support. There's also a large number of compressors that are supported by MyTile, ZSTD, LZ4, run length encoding, and more that InnoDB don't support. There's also significant reduction in write amplification. So we do not have a redo log or an undo log like InnoDB. So MyTile has a much less overhead for the write amplification that exists. We also natively support the time traveling without the need for system version tables or any outside libraries or tools to support that time traveling. And we also believe that compared to InnoDB, we're going to have much better performance at the terabyte scale. That large data sets are really what we target with TileDB. Although TileDB scales, from kilobytes to terabytes or petabytes, compared to InnoDB and the general use cases, we're really targeting the larger data sets. Now, there are some disadvantages of MyTile, of course. InnoDB is very mature, very battle tested. Like I said, it's been around for quite a while, used in probably millions of servers worldwide. So InnoDB has been around quite a while. InnoDB also has great support for replication and backups through tools like Maria Backup, Extra Backup, and Galera for cluster type environment. And InnoDB also has significantly better single record insert performance. Like I say, that transactional workloads that InnoDB really excels at, that we're not really geared MyTile toward. Now, of course, with these disadvantages, MyTile does support single record inserts. We've talked about how to do backups, and we do use MyTile in production today. So the fact that it's not quite as mature as InnoDB does not prevent anyone from using that in production. But InnoDB does have certain advantages for certain use cases, for sure. Now, let's compare to MyRocks. MyRocks is now pretty much the de facto standard for large data sets in TileDB. Large data sets in MariaDB. Since TokuDB has been deprecated and being removed from MariaDB, MyRocks is kind of the de facto standard to compare to. So some of the advantages of MyTile is we have cloud native support again, so you store that data on S3 or blob stores. There's also large interoperability with TileDB integrations or APIs. So that means that, with MyRocks, it's based off RocksDB. But there are some semantics that are involved there, so you can't quite query the underlying RocksDB key value store from outside of MariaDB, or it's not very common to. But with the MyTile, it's the native TileDB format. There's no special format, no semantics, and you can just query that array directly from MyTile or from anywhere outside of MyTile without any problems. There's also some differences in compressors offered between MyRocks and MyTile. We have some additional encoding, such as run length encoding, double delta, and several others. Now, of course, there's some disadvantages too with MyTile. MyRocks is more mature, and it supports additional things in MariaDB for statistics and parameters. MyRocks has a lot of built-in support for things like the performance schema and other statistics in MariaDB. TileDB itself has internal statistics, but not all of those are plugged into the performance schema and things like that. MyRocks also supports MariaDB transactions and checkpoints, where, like we said, MyTile does not, although MyTile does not necessarily have a need for the transactions to get the same level of ACID compliance that MyRocks does. So I'd also like to talk about a couple of use cases of MyTile that we have today. So the first one is we have a customer in the geospatial domain that has AIS location data. That's the lat long and other information about a ship. They store this data in sparse TileDB arrays today. And they have employees that access the data via a number of methods, including from Python directly, from MariaDB, and from the embedded MariaDB. And the great thing here is the employee can pick the tool they want for the job. From Python, they might be using the embedded MariaDB instance to run SQL queries directly. Maybe they're more comfortable with SQL than they are with Python, or they have a better familiarity with how to use bounding box queries and certain things in SQL, so they're able to do that. Or, also if they're trying to integrate maybe with some sort of mapping software, or maybe Pandas, data frames, or something else, they can use Python and access the TileDB API directly and use array semantics to access that. But the real power here is that the TileDB array can be accessed by the best tool for the job, or whatever the user is most familiar with, and they're not bound just to the SQL query. If they need a different type of integration, it is available to them. The other use case we want to highlight is a time series data set. So we have a customer that has a common time series data set of stock market and asset trading. They store the data in sparse TileDB arrays, and they use the embedded MariaDB to allow that fast and easy data exploration. So they're able to run queries directly from a Jupyter Notebook or from the laptop to explore the data and make some initial testing of maybe machine learning algorithms or something. Now, for their large jobs, they tend to use Spark or Dask or some other tool to run large distributed queries, which is great because we have the interoperability to do that on the exact same data set. But an interesting note about this customer is they've actually experimented with running distributed SQL queries via a cluster of independent MariaDB servers. So they spun up a handful of MariaDB servers. There's no cluster, no Galera, no communication between them, no replication. And at the application layer, they shard the query ahead of time and issue it to all the MariaDB servers in parallel. And because everything's lock-free, multi-reader, multi-writer support, they can run that computation in a largely distributed manner and then collect the results back at a single client. It's a very interesting use case and some of the flexibility offered by MyTile and some of the advanced use cases. And I look forward to working more with that customer and experimenting more with things like Spider to do some of the sharding in a more automated fashion. So besides just our customer use cases, I want to talk a little bit about how we use MyTile internally to TileDB. And to do that, I want to highlight again that at TileDB, we have two different products. We have the TileDB Embedded, which is a fully open source storage library that's built on top of MyTile, and we've talked about here. And we also have TileDB Cloud, which I hinted about before, which is our SaaS offering of a hosted solution where you can do access control and sharing and have hosted notebooks and serverless computations via both serverless user-defined functions in like Python or R and serverless SQL. And that serverless SQL is powered by MariaDB and the MyTile storage engine. So we run a variety of MariaDB servers in an auto-scale cluster in an auto-scale manner, and we allow the user to query their data set remotely with simply just the string of the SQL. So here I have a little snippet of Python code where they're going to access this data and perform some sort of aggregation. They just give us the query, and what happens is that string is taken, shipped to MariaDB in our service. We run it, and we return the results directly to the user. It can be returned as a Python, as a Pandas data frame in Python, or as JSON in any other language, or the user has some options depending on what they're trying to do. But the real benefit here is the MyTile storage engine is able to be used in this manner for this serverless SQL integrations that we have. It works, from a client perspective, it's very similar to the embedded offering of MariaDB. They just give a SQL query. They don't worry about running a server and maintaining the server. They're able to access remote data sets simply on MariaDB by issuing the query. The main difference and benefit here with the serverless SQL is you're not pulling the data down to your machine. So if you're on your laptop, you don't have to worry about pulling the data across the internet. You don't have to worry about the memory requirements on your machine. All the resources and connectivity is handled in the TileDB Cloud product itself. So that's it for the introduction to MyTile here today. I thank everyone for their time. We look forward to continuing to work on MyTile, to upstream it to MariaDB itself, and work with the wonderful folks at MariaDB to continue investing and promoting in MyTile. We hope that you found some of the use cases interesting, and we're very happy to answer any questions and to discuss more about MyTile and TileDB in general. Feel free to reach out to us at any of the contact information you see on the screen. We look forward to talking about MyTile more and discussing in detail with everyone here today. Thank you again.
Seth Shelnut, great presentation. Good evening, Boston.
Thank you for having me today.
Great, yes. So, how is it different to give a presentation in New York from giving one in Paris? You already gave that one yesterday, didn't you?
I did, yes. I'll say the time being in the afternoon today instead of earlier in the morning, a little nicer, but I think, day two goes well, right?
Yes, thank you. So, I've been speaking around with people, and I'll try with a very basic question to begin with. Like when you look at something new, you need something else to compare it to. So TileDB, how do you compare it to Parquet? Is that a fair thing to compare it to? And then also MyTile. People tell me that I should compare it with the new S3 storage engine that we've also featured here at the MariaDB Server Fest. So what's your take?
Well, I think those are two great questions, and I'll take them as two separate questions and try to answer them a little succinctly. TileDB does compare to Parquet. Parquet is an Apache project. Most people probably use it with Spark and Pandas data frames and some couple different applications there. But the Parquet format has a couple of downsides. First off, it's only a format. There is no uniform storage library with it or storage system with it. So every application has to implement layers on top. For instance, Spark might implement its own partitioning compared to like PrestoDB or what some Python libraries do. And we're seeing some of these downsides now start to culminate in additional applications like Delta Lake, Iceberg, Hootie, all of these applications being built on top to kind of fill in the missing gaps of Parquet, where we would say TileDB has those gaps filled in already. We support multi-dimensions, we support indexing across multiple columns, we have time traveling capabilities, multi-reader, multi-writer, and we support a variety of cloud environments, all within a single embeddable C++ library. And that single embeddable C++ library kind of leads us to the second question about how do you compare it to the S3 storage engine? Well, the S3 storage engine that came about in 10.5 is mostly for archival purposes. There is some plans there to do different things, but it's really geared toward the archive, as we heard a presentation earlier today about that, a wonderful presentation given, where MyTile is designed for read and write support built on top of that embeddable TileDB C++ library. So MyTile gets all the features that the TileDB library has itself. Multiple cloud object stores, Google Cloud, Azure, S3, along with that multi-reader, multi-writer support and the high level of parallelism. So we think the use case is a little more broad than the S3 storage engine, as we do support pretty much all types of OLAP use cases.
Good. So I think that was a clear answer. So then MyTile, secondary indices, do you support such a thing?
So today, TileDB does not support secondary indexes. It is on our roadmap of things to consider in the future, but for today, we only support indexing on what we call the dimensions. And the dimensions in TileDB can be one or more fields that define the sort order of the multidimensional array. So they work very similar to a database index, but the differences kind of come in with the fact that you can query on dimensions without needing to query across all dimensions. Of course, performance is greatest when you have a full key, to speak in MariaDB terms, but you can query on a subset. And I think that's where we don't support secondary indexing, but we do support things like condition pushdown to try to take advantage of that.
And can you expand on this idea of condition pushdown? I mean, we do have it in several other engines in MariaDB as well. So is that something that substitutes for the need for using secondary indices, or how do you view the condition pushdown?
Yeah, so the condition pushdown, and I believe there was a presentation earlier on the Connect engine, which does support pushing down those filters to other libraries and other databases. It kind of works in a similar manner with TileDB, where in MyTile, where there's certain conditions and predicates that might be across different dimensions that we know that in TileDB it can handle and can optimize a query for. So we take those conditions that MariaDB gives us, and we push those to the storage layer in TileDB. And the query optimizer from MariaDB generally does a fantastic job. And it's definitely a great piece of software, and it's got a lot there. But sometimes it assumes that the indexing is based off traditional MariaDB indexing. And since TileDB is a little bit different, there are certain cases where it might not issue an index query, where we know that TileDB can actually do a much more performant query of the data than like a full table scan. So we use that condition pushdown to intercept any type of predicates or operations or filters that we know TileDB can handle in a more efficient manner.
Mm-hmm. So what about the sizes here? Are you specialized in some certain data set sizes, or is it sort of generic?
Yeah, so the great thing about TileDB is it scales from data sets on your laptop to terabytes and petabytes of data in TileDB cloud. In the cloud. And TileDB handles that natively with the same library, the same system. However, we're really geared toward, and with MyTile, what we've been testing with and with our customers is the larger data sets. Really, once you start getting to the tens, hundreds of gigabytes and terabyte size, that's where we've really been focusing a lot of our performance efforts and optimizing for these large data sets. Although it's very possible to start with a small data set and scale linearly. It's one of the nice benefits of TileDB.
Mm-hmm. Interesting. So, by the way, on Zulip, we had quite a number of questions in many sessions. So, did you get anything interesting that you want to present to everybody here of your questions on Zulip?
Yeah, I think there was two very interesting questions, which I'll cover quite quickly. The first was one from a few minutes ago asking about how the time travel support worked. And I think one of the things I want to highlight about MyTile is that we've worked to extend the MariaDB storage API in all the manners that they provide to add table parameters or session parameters or query parameters where possible. So the time traveling is just simply a table parameter that you can add to be able to select your timestamps. And for a variety of the different fields, such as compression that you might want to do if you're creating a new table, we just extend the natural offerings of MariaDB. So that works well. And later on, we'll provide links to all the documentation where you can see all the exact parameters and things like that. Mm-hmm. Another question that we had yesterday, which I'd like to answer today very quickly, was I believe it was Vincenzo asking about how we support S3. And that really I want to highlight again, emphasize that our S3 support comes from the TileDB storage library. So as the TileDB storage library evolves over time, and we add additional backend support, such as maybe Alibaba Cloud or some of the European providers, or even earlier today, we saw a wonderful presentation on SSD optimizations with some computation pushed to the SSDs. Anything like that, if we ever support stuff like that in TileDB, MyTile just naturally will inherit all of that functionality as we go.
Good job. Excellent. Good, great answer. So thank you, Seth Chelnut, for a great presentation and good answers.
Thank you very much for having me. It was wonderful to be a part of this.
So that was it for today. I hope you liked it. If you did, feel free to share it on social media, LinkedIn, Twitter, hashtag MariaDB Serverfest. And tomorrow we'll continue. I would say same time, same channel, but the channel won't be the same. There's a new YouTube link, and you'll find it on mariadb.org/fest2020. So see you tomorrow.